While the entire world, with anticipation and excitement, marks the completion of another milestone in interstellar travel, the appearance of the third interstellar ship, named Tri-Atlas, on the horizon, hidden events are unfolding that we barely suspect. These events could prove to be far more significant and dangerous than they initially seem. Only now, after careful analysis, have we noticed a troubling trend concealed behind the noise of news reports and headlines. In the sky near our planet, a comet is slowly but steadily approaching, accompanied by bright bursts of cosmic particles and gases. It is moving toward Earth, and its path appears much closer than the safe range our eyes and telescopes typically monitor. This celestial visitor slipped past our instruments as if it were an unnoticed guest hiding in the shadows. No telescope managed to detect it until it was obscured by the sun's brightness. Only after some time, when the sun's rays shifted position, did we notice its approach. By October 20, 2025, about 8 days from now, it will reach the so-called closest approach to Earth, the point of minimum distance. At this moment, a crucial question arises. What does this mean for us living on Earth? How dangerous could this celestial object be? Is its approach a real threat to life and safety? Or perhaps, everything is much simpler and less threatening than it appears at first glance? Stay with me until the end, and you will realize that the threat discussed in newspapers and news broadcasts is something we almost didn't notice. The true danger, the one capable of destroying our world and altering humanity's fate, is hidden much deeper and closer than it seems at first glance. Perhaps it lurks in the shadows of information noise and remains invisible to most. If these thoughts and concerns resonate with you as strongly as they do with me, don't forget to share your mood, perhaps by liking this post, and to follow upcoming developments carefully. Time is moving quickly, and everything happening is unfolding in real time. In the future, we may need to discuss and share our thoughts and comments, indicating where exactly you're following the news from, what time it is now, and whether you believe we will ultimately uncover the full truth about those discoveries that have radically changed our perception of the world. And if you'd like to support the development of this project or community, share this information on your social networks, whether it's X, Facebook, Reddit, or through group chat platforms, because, thanks to your support, we can continue investigating and reporting on such important and mysterious events. Your help not only keeps us connected but also actively assists in uncovering the truth about the mysteries hidden in space. Now, let's take a closer look at the current situation with interstellar objects. The whole world is today practically shouting about the three Atlantes, as these mysterious celestial bodies are called. Headlines in news feeds are usually shrouded in secrecy and mystery, creating an impression among readers that they are witnessing something incredible, unknown, and dangerous. Debates and theories are heating up on social media, while scientists and astronomers are doing their best to reassure the public. There is no real threat to Earth from these objects. They assure that these three interstellar visitors, like travelers from other worlds, will pass by our planet at a safe distance, approximately 1.8 astronomical units, about 167 million kilometers. This distance is far enough not to cause concern, according to experts. Orbital trajectories have confirmed that these interstellar bodies do not pose a threat. NASA and other space agencies have clearly stated that we usually do not encounter comets as depicted in science fiction stories or space novels. In reality, when it comes to discovering these mysterious celestial objects, we mainly rely on ground-based optical telescopes that continuously monitor the sky, capturing faint points of reflected sunlight. Thanks to these instruments, we search for signs of comets, which often appear as tiny, barely noticeable spots of light amid the vast expanse of the sky. However, sometimes some objects, such as R2, remain invisible to our entire observation system. Why does this happen? It all comes down to a phenomenon that scientists have called the holocheck or Holoc blind spot effect. This effect is a specific region in the sky where objects can exist, but due to their position and brightness, we simply cannot see them. These invisible points to our instruments are like ghosts. They exist, but we know nothing about them until it's too late to do anything. Comet R2 appeared on our radar and optical screens only after it passed perihelion, the closest point to the Sun in its orbit. This happened on September 22 of the 12th year, when it was already moving toward our planet. At that moment, its distance from the Sun was about 50 million kilometers, which in astronomical units was roughly half. This distance is large enough to cause significant heating of the comet's surface and trigger the sublimation of volatile substances. It is these substances, when evaporating, create the characteristic cometary atmosphere, a cloud of gas and dust surrounding the comet, known as the coma. Part 3 of 57. When the comet approaches the Sun, its surface begins to evaporate intensely, resulting in the release of gas and dust into the surrounding space. By the end of September, observers using both ordinary telescopes and more sensitive instruments recorded a sharp increase in the brightness of this celestial body. During this period, the comet's brightness reached about 6.5 on the known scale, where lower numbers indicate brighter emission. It was at this moment that it became visible that an expanding cloud structure, the coma, was forming around the nucleus. Photographs showed a bright greenish halo, indicating the presence of diatomic carbon and cyanogenic radicals, which, under the influence of solar ultraviolet radiation, began to fluoresce, creating the characteristic green glow. The comet's tail, stretching several degrees across the sky, was visible even with binoculars, if one knew where to look. This is a fairly long and bright luminous structure, indicating the direction of the comet's movement and evidencing powerful emissions of dust and gas. But there is an important point that raises additional questions. The size of nucleus R2, its structure, as well as its current rotation state, remain unknown. We cannot say for certain whether it has broken apart or might do so in the near future. Comets are highly variable and capricious objects. They often shed chunks, split into separate fragments, or disperse debris along their orbit. If, during a close pass or for other reasons, R2 begins to disintegrate or split, small fragments detaching from the main body could deviate from the original trajectory. This, in turn, would create what is called a potential intersection cloud with Earth's orbit. Currently, the minimum distance between R2's orbit and our planet is estimated at approximately 48 thousandths of an astronomical unit, which in kilometers is about 7 million. In cosmic scales, this is a very small gap, like a thin thread stretched between the heavens and Earth. It is at this distance that potential danger exists. However, it is important to emphasize, I do not intend to claim that the three atlases are, in essence, a secondary matter, merely part of a game played by our minds. They can be imagined as the hand of a magician waving in the air, distracting our attention while the real miracle happens somewhere else. The main trick is precisely R2, and all our current work is dedicated to it. So, let's start by examining the distraction caused by the three-eyed atlas and try to explain why it is safe and in no way poses a threat. After that, we will delve into everything we know about R2, as well as consider areas where our information is still insufficient. We will not overlook the potential scenarios of possible risks: dust trails, fragments, meteor swarms, all those elements that could cause concern or alarm. We will attempt to compare these situations with past dangerous incidents, where we barely managed to notice the threat because the objects slipped past our defenses just days or even hours before we could detect them. Ultimately, we will discuss what to pay particular attention to, what exactly you should demand from the institutions responsible for tracking such objects, and what happens when detection systems fail. Failures that occur much more often than people tend to think. When this happens, what leaks out is not always what you were observing or expecting to see. The second part of our discussion will focus on the mechanics of discovery. Why was it Swan who managed to detect this object, while ground-based research did not? Typically, comets are discovered using optical telescopes that scan the night sky. These instruments look for faint points moving among the stars, which become more noticeable as they approach the Sun. Their ice sublimates, and they develop a bright tail. We have been working with this method for over a century, and it is considered quite reliable. However, there are cases when it fails. It is precisely in such moments that an unconventional detection method comes into play, for example, using special detectors that register hydrogen emissions. Thus, Comet C. 2025 R2, for instance, was not detected by traditional optical means. It was spotted on board a spacecraft equipped with a detector designed to observe hydrogen emissions. This instrument is called SWAN, which stands for Solar Wind Anisotropes, and is part of the SOHO mission launched in 1995. The primary purpose of this device is to produce images of the solar wind by detecting hydrogen Lyman alpha radiation in the ultraviolet range. Hydrogen that glows at a wavelength of 121.6 nanometers is invisible to the human eye but appears brightly in ultraviolet light. When comets approach the Sun, their ice sublimates, and the resulting water vapor breaks down into hydrogen and oxygen. The hydrogen, in turn, disperses around the comet in a vast cloud, much larger than the visible coma. It is this hydrogen vapor, produced by sublimation, that can be detected millions of kilometers away from the object, even when optical telescopes show no signs of a comet. This is not new. Over the years, the SOHO mission and its SWAN instrument have detected thousands of comets. Most of them are small objects that pass close to the Sun and eventually completely evaporate. However, R2 is a completely different case. This is most likely a guest from the outer part of the solar system, possibly a nebula, moving along an elliptical orbit, approaching our star and then receding back into deep space. This object leaves no noticeable traces for ground-based observations, and the reason for this is its position. The Sun occupies a very bright spot in the sky, and its light interferes with our telescopic observations. Astronomers use a special term, the Holtec effect or the Huygens blind spot, to describe the complex and sometimes mysterious nature of observing celestial objects. Depending on which historical figure they prefer to consider the source of this phenomenon, they use one term or the other, but the essence remains the same. In a certain area of the celestial sphere, as if in a dead zone, objects disappear from view, becoming invisible to us like ghosts hiding behind an unseen curtain. It is precisely in this zone that the region of space becomes particularly difficult for detection and tracking, as objects seem to dissolve into the darkness of space, leaving only faint, barely perceptible traces. This time, it was exactly there, in this mysterious region, that the R2 astronomical system reached its perihelion, the closest approach to the Sun, at a distance that can be imagined. This event occurred on September 25, 2025, when it completed its last orbit around our star, passing at about half an astronomical unit, roughly 75 million kilometers. For several weeks prior to this moment, as well as afterward, this object remained invisible to most optical observations. When it finally emerged from the bright solar glare, the perihelion had already passed, and its path was heading toward Earth. It was then that, thanks to the attention of amateur astronomer Vladimir Bazuga, something unusual was noticed in the data about flying waterfowl, swans. A detailed analysis of archival ultraviolet images, taken with specialized instruments, revealed a characteristic hydrogen glow, indicating the presence of a comet or another cosmic object. Vladimir detected a moving spot, a small cloud that shifted and changed position over time. He recorded this phenomenon and began checking with other observers to confirm it. Soon, optical confirmation followed. It turned out that this object indeed exists in reality, and it is a comet. However, by the time this was confirmed, we had already lost several weeks of observations that could have provided a more complete picture of its behavior. After all, during that period, we lacked data on how exactly the comet was preparing for perihelion, how it was brightening or dimming, how its orbital trajectory might have changed, and whether it was disintegrating or not. These are important points, because errors in detection act as a strict filter through which all our knowledge of space passes. Optical observation methods have their limitations, the faintest star magnitude they can detect, as well as gaps in sky coverage caused by weather conditions, clouds, bright sunlight, and other factors. At the same time, instruments designed to measure hydrogen in the ultraviolet range, such as SWAN-type devices, have varying sensitivities and possess blind spots. They can detect objects that escape optical telescopes because they operate in a different wavelength range and have different capabilities. However, these tools are not universal sky surveyors. They are specialized, created for specific tasks, and therefore detect only those phenomena they are intended for. As a result, a comet that might be visible in the optical range sometimes goes unnoticed or is discovered too late, while objects hidden in the blind zones of instruments remain out of sight. The consequences of such late detection are extremely serious. The fewer observations we have, the greater the uncertainty in determining the object's orbit. Astronomical mechanics requires high precision to predict the future trajectory. Calculations take into account not only gravitational influences but also non-gravitational forces, such as gas emission or other processes affecting the object's movement. In the case of R2, it was discovered late, and therefore its orbit was uncertain. Even weeks after its detection, the margin of error in calculations remains significant. We are often overwhelmed by everyday hustle and bustle, and we completely overlook the amazing things happening around us. This continues until a casual amateur astronomer, using sophisticated instruments aboard a spacecraft, detects unusual radiation in archival data, apparently originating from hydrogen. Only then do we face the question: how many similar objects have we missed? How many comets, passing by us, are currently crossing the boundaries of our solar system? And the answer to this question is not straightforward. Most of them remain invisible to us because they are not in the right place at the right time. We cannot know their exact locations, and this is perhaps the main problem. The issue lies in our insufficient ability to detect these cosmic visitors in real time. Next, we will try to trace what exactly happened with the so-called R2 object from the moment of its discovery, what unusual and remarkable events are associated with it, flares, strange structural features that make this comet something more than just an ordinary icy fragment. This is the third part of our story, in which we will examine in detail what truly happened to this celestial body. Let me take you through the chronology of events to make it easier to understand how observations and discoveries developed. It all began when one of the Russian amateur astronomers, Vladimir Bezugi, on September 11, 2025, noticed a moving source emitting hydrogen in archival images taken from an orbital platform. He detected it in the region of the Cygnus constellation. The object was temporarily designated C-2025-R2, where the letter R indicates that the discovery was made in the second half of the month, and the number 2 signifies that this was the second comet discovered during that period. This was an important moment because optical confirmation quickly followed. Ground-based observers, equipped with telescopes, swiftly redirected their instruments toward the identified coordinates. As a result, they managed to capture a blurry spot, a faint glowing coma, a small luminous cloud in the pre-dawn sky, which confirmed the presence of a comet. The next significant milestone occurred on September 12. That day, the comet passed perihelion, the closest approach to the Sun, at a distance of approximately 0.55 astronomical units. This distance, comparable to the space between Earth and our star, was close enough to activate internal processes within the comet. As a result of sublimation, the transition of ice and volatile substances from solid to gaseous state, water vapor, carbon dioxide, methane, ammonia, and other volatile components began to be released. These substances, transported within the comet, started to escape outward. It was at the end of September that observers first noticed signs of activity. The comet suddenly became brighter, and its apparent magnitude sharply increased. Some sources indicated that its brightness reached about 5.9, while others reported 5.6. This magnitude is logarithmic, meaning even a small change in the number signifies a very significant increase in brightness. The expansion of the coma became evident. A characteristic greenish glow appeared around the nucleus in photographs, resembling an halo, which indicated the presence of diatomic carbon molecules fluorescing in the ultraviolet spectrum. This phenomenon is quite common in comets and is related to carbon compounds sublimating from the nucleus, becoming ionized under solar radiation, and then fluorescing, emitting a greenish glow. Such a sight seems almost extraterrestrial, but it is merely a manifestation of chemical processes occurring in space. Another notable feature was the comet's tail, which took on an asymmetrical shape. Some images suggest that Comet R2, apparently, produces many large and noticeable grains of dust. These large particles, forming in its coma, create certain effects that cannot be ignored. Primarily, the presence of such massive grains indicates that the comet's nucleus itself is losing large chunks. Part 8 of 57. It may be about fragments that detach from the surface or smaller particles that chip off under the influence of internal stresses caused by intense heating or thermal shocks. If these fragments are large enough, they can remain as separate objects, each with its own trajectory, different from that of the parent comet. As a result, such large debris can disperse throughout space, forming a field of various fragments spreading in different directions. This phenomenon is often observed in comets when debris begins to spread from the main body, creating characteristic fields of dispersing particles. A particularly vivid and striking image of this process appeared on a website dedicated to astronomical photography on September 28, 2025. It depicts a comet with a green coma, standing out brightly against the twilight sky, with its tail stretching upward like an outstretched hand reaching away from the brightly shining sun, hidden behind the horizon. At the moment of the photograph, the comet was still very close to the horizon, making it difficult to observe because it was hard to see with the naked eye. Nevertheless, it was still possible to spot it, as photographers and astronomy enthusiasts captured images, some with binoculars, others with small telescopes. These photos show the comet's tail stretched across several degrees of the sky, appearing as a thin, ghostly ribbon that seems to extend along the dark night sky. This scene creates the impression of a light, almost weightless stream of gas and dust slowly spreading across the sky, forming the characteristic atmosphere of a comet. However, there is an important nuance to consider. Predictions regarding the brightness of comets are, as is well known, not entirely precise. There are many factors in astronomy that make forecasts of a comet's luminosity quite unreliable. Comets are highly unpredictable objects. They do not follow simple patterns. During their passage through the inner parts of the solar system, they can suddenly explode their shells, disappear, or fragment into numerous pieces. Their brightness depends significantly on which part of the surface is actively sublimating, that is, transforming from a solid into gas, and this process, in turn, depends on many factors: the size of the nucleus, its composition, rotation speed, and the degree of heating by sunlight. Nevertheless, despite these complexities, astronomers make well-founded assumptions and models. Still, it's important to remember that comets love to surprise us at the most unexpected moments. According to preliminary forecasts, under favorable conditions, the brightness R2 could reach approximately magnitude 4, making it quite visible to the naked eye during the dark hours of the night. This level of brightness allows it to be observed even without special instruments when the light of the moon and city lights do not interfere. On the other hand, there are more conservative estimates suggesting that the comet will not reach such brightness and its magnitude will remain around 6. That is, a level at which binoculars or a small telescope will be necessary for observation. As of today, October 10, 2025, the registered apparent magnitude of the comet is approximately 6.7. This means that it is currently slightly below the naked eye visibility threshold, especially under urban light pollution or faint night skies. Nevertheless, there is hope that as it approaches its period of maximum activity and under favorable weather conditions, the comet may become brighter. Whether its brightness will increase further depends on whether a sudden outburst occurs within the nucleus. The possibility of various natural and cosmic phenomena related to icy formations often arouses both scientific interest and concern among curious observers. One such phenomenon involves underground pockets of water ice, mysterious cavities that can suddenly be exposed to sunlight or other factors. Imagine, within these icy traps, small reserves of water could be hidden, which might suddenly awaken and start melting when exposed to sunlight. This not only creates new forms of icy structures but can also lead to the destruction of surrounding formations, the formation of cracks, or even the release of gases trapped inside. All of these are potential consequences of a single unexpected event. And what is especially alarming is that such situations have already occurred once before, and it is quite possible they could happen again, particularly if these processes occur at an inopportune time, such as when a comet is near Earth. If, at the moment of its disintegration, the comet is sufficiently close, the fragments dispersing in all directions will form a dense cloud of debris. In this case, despite the scale and risk involved, there is a chance to pass through this cloud without harm. Later in our discussion, we will move on to more precise figures, orbital data, distances, velocities, and geometry, since these parameters help determine whether such an event is merely a matter of curiosity or a serious threat to our planet. This is part of a series where we will focus on the most accurate calculations and models to understand the reality of what is happening. Let me begin with a geometric picture of the movement. So, we are talking about a comet named C-2025-R2. It moves along a highly elongated, nearly parabolic orbit around the Sun. This is indicated by its eccentricity, which is approximately 0.99990362929. This value is very close to 1, indicating that the orbit is nearly parabolic, but still slightly more than perfectly parabolic. In astronomy, an eccentricity equal to 1 signifies a trajectory that is exactly a parabola. That is, an object coming from infinity and then disappearing without a trace into the distant reaches of space. At the same time, a value just less than 1 indicates that the comet's trajectory is an extremely elongated ellipse, which, in the absence of interference, could exist for tens of thousands of years. Regarding scale, the semi-major axis of this comet's orbit is approximately 798 million kilometers, which in astronomical units is about 47, more precisely, 48, times that. This means that the farthest point of its orbit is called the aphelion, a distant, almost unreachable point located beyond the Kuiper belt, deep inside the Oort cloud. This region is considered one of the most remote and mysterious in our solar system. The orbital period of the comet is estimated at roughly 22,554 years, meaning it completes a full orbit around the Sun over such a lengthy period. The comet last visited the inner solar system during the late Paleolithic era, when humans were already drawing images of their hunts on cave walls and searching for mammoths. Events far removed from modern times in terms of chronology. The inclination of the orbit relative to the plane of the ecliptic, that is, the plane in which Earth and most planets orbit, is approximately 44.5 degrees. This means the angle between the comet's orbital plane and Earth's plane is minimal and is about 44.5 degrees. Most comets originating from the Oort cloud arrive with much steeper inclinations, plunging through space at random angles. However, the key parameter that plays a decisive role in assessing potential danger is the so-called miss distance, the minimum distance between Earth's orbit and that of the comet. This measure is determined through geometric calculations and does not account for temporal factors, assuming that both orbits could intersect at the same point simultaneously, without considering their movement over time. In the case of the comet's orbit, R2, the miss distance value is approximately 0.048 astronomical units, which is roughly 7 million kilometers. In other words, if you were to draw both of these orbits in a three-dimensional model of space and measure the shortest distance between them, you would get exactly this gap, 7 million kilometers. This is precisely the gap that causes concern. Understanding this interval is very important because if Earth and the comet were to be in the wrong positions along their orbital paths at the same time, the gap could reduce to zero, making a collision unavoidable. However, current orbital calculations show that on October 20th of this year, Earth and comet R2 are approximately 39 million kilometers apart. This means the comet will pass by without hitting our planet, and this time we will be safe. That is what the models indicate and what our calculations confirm. Currently, NASA is not issuing any warnings about a potential threat, no alerts, there is no danger. Nevertheless, the question arises: why do we continue to discuss this topic and talk about possible danger? The answer lies in the fact that current orbital solutions, despite their accuracy, are never perfectly flawless. They are based on observations, and any observations are always somewhat uncertain and approximate. The more observations we have and the better their quality, the more accurate our calculations and orbital modeling become. However, with Comet R2, the situation is such that it was discovered quite late, and we have fewer observations than we would like. Therefore, the comet's orbit is currently constrained within certain parameters, and although we can say it is sufficiently well defined, absolute precision has not been achieved. Even the slightest perturbations, non-gravitational forces arising from gas release from the comet's nucleus, changes in its rotation, or redistribution of its mass can slightly shift its trajectory. The magnitude of this shift may be just a few thousand kilometers, which, on one hand, is not critical for the main nucleus of the comet, but on the other hand, is very important if debris or fragments are to be released. These particles can vary in mass and velocity, and if the comet breaks apart or has already disintegrated, the fragments will begin to disperse along different orbits. The larger the fragment, the smaller the difference in its velocity and, consequently, the less dispersion along the orbit. Small shards, dust, and gravel can spread over very large distances. If Earth passes through such a stream of cosmic debris at that moment, we could witness an increase in meteor activity, a possible meteor shower, or even more serious phenomena, such as a meteor storm, and in the worst case, something significantly more dangerous. As of today, the brightness of Comet R2 is approximately 6.7 magnitude as of October 10, 2025. This is much dimmer than previously assumed, and the reason is clear. Comets fade as they move away from the Sun, losing their brightness. The main question now is whether the comet will experience a new outburst of activity. If it suddenly becomes significantly brighter, it will be a signal of renewed activity, possible fragmentation, or the release of new volumes of volatile substances. Such a scenario will undoubtedly change our risk profile and require a reassessment of the entire hazard evaluation. To better understand the situation, it is helpful to imagine the positions and movements of these objects in space. At the center is the Sun, and around it orbit the objects. They wobble, crack, and pieces break off from them, which do not always follow the original trajectory. These fragments, like unruly particles, drift through space, spread in different directions, and sometimes suddenly appear on the sky when least expected. This is precisely the phenomenon we are talking about when we refer to the theater of space observation, a public spectacle that simultaneously attracts attention and distracts from deeper issues hidden behind the brightness of stellar events. In this article, we will try to explore how media coverage shapes what we focus on, as well as discuss the theater of the near future, how public attention is concentrated on showy spectacles that divert from more complex and important topics. Let's start with the fact that October in the sky turns into a true kaleidoscope of events. It resembles a crowded sky filled with bright points and moving objects that catch the eye and inspire admiration. In the middle of this month, two comets approach Earth, C. 2025 R2 and C. 2025 A6, which is also called Lemon. Both, like two bright guests, are approaching our planet and reach their peak visibility around October 20th. These comets not only excite amateur astronomers but also create a unique spectacle. They seem to move toward each other, approaching at a minimal distance of just a few days. This rare phenomenon is seldom observed in nature, which is why it attracts such widespread interest. All of this transforms into a real celestial performance that makes people look up, beyond the horizon, in hopes of seeing something unusual and beautiful. But not only comets attract our attention in October. During this period, an annual meteor shower called the Orionids also occurs. Its peak falls around October 20th-21 stone, precisely when Earth crosses the trail of Halley's Comet, the famous comet that appears in our sky roughly once every 76 years. Even when it is far away and seems unreachable, the trail it left millions of years ago continues to spread along its orbit, forming a stream of dust and tiny ice crystals. Every autumn, our planet crosses this stream, and particles entering the atmosphere at a speed of about 70 kilometers per second burn up, creating bright streaks of light, meteors, or shooting stars. During the peak of this meteor shower, one can observe from 10 to 20 meteors per hour, and sometimes even more. This is not a particularly powerful phenomenon, not a storm that would flood the sky, but it is reliable and predictable, which makes it popular among astronomy enthusiasts. So, on the night of October 20th, two comets, R2 and Lemon, along with the Orion meteor shower, which reaches its peak, will create a spectacular display in the night sky. The sky will be literally filled with bright points, moving light streaks, and shimmering comets. At this moment, media coverage will reach its peak, and astronomy lovers and casual skywatchers will begin sharing photos and impressions on social networks. News agencies will publish reports about the upcoming show, making this moment especially noticeable and memorable. This is a situation where anyone can participate in a public observation of the celestial spectacle, and, not without reason, use it as a distraction from more complex or unpleasant topics. While everyone is looking up at the bright comets and meteors, few ask questions about how close these celestial objects are to our planet and what their actual danger might be. For example, a detailed article in the Washington Post described how both comets, R2 and Lemon, arrived from a distant star system, like uninvited guests from the depths of space, whose unusual story instantly attracted the attention of scientists and astronomy enthusiasts. At first glance, this object seems simple, but with each new observation, its nature becomes more mysterious. Its color varies. Sometimes it appears bright red, sometimes vividly green, depending on which observation sources or spectral ranges researchers trust. Such color changes seem strange and unusual, because asteroids and comets usually maintain a stable appearance and do not change color drastically. Here, something clearly goes beyond the usual characteristics, which has sparked many hypotheses and assumptions. Some scientists suggest that this object may be capable of changing color or appears to do so because its surface or composition could be unusual, or due to features of its trajectory and illumination. It is quite possible that observers are experiencing optical illusions caused by observational peculiarities, but intuition suggests that there is something else going on. All this evokes associations with how asteroids or comets behave. Usually they move along predictable orbits, and their trajectories can be determined with high accuracy. But this object behaves differently. It changes color, seems alive, and its behavior goes beyond the usual scenarios. These unusual properties sparked a wave of speculation about its origin. Some experts hypothesize that it is of artificial origin, possibly an alien probe or device created by intelligent beings. Such ideas are based on the trajectory of this object, which appears to be encoded or encrypted, resembling a message hidden within its movement. Rumors also circulate among scientists that messages or signals could have been encoded in its trajectory, transmitted through some unknown channels. However, most experts remain skeptical of these claims, considering them unlikely, as there is currently no convincing evidence to support such a hypothesis. Nevertheless, all of this remains a fascinating mystery that evokes strong emotional excitement and a desire to understand what is happening. Meanwhile, alongside this enigmatic object, a more familiar and recognizable visitor appears in the scientists' field of view, R2, with an uncertain orbit and a history of flares that sometimes flare up and then disappear. It does not generate the same buzz as the first object and is perceived as less exotic. This object originates from our own solar system, most likely from the Oort cloud, a vast and distant shell of icy bodies beyond Neptune's orbit, which serves as the source of long-period comets. In this case, it is a typical space object not associated with interstellar travel. It is simply another comet that occasionally passes through our region, sparking interest and wonder but not causing such intense emotions. But even in this case, things are not so straightforward. The comet in question is special because we have not seen it before. It only made an impression on us when it was almost directly above us, in close proximity to our planet. This is one of the rare comets that was hidden in the sunlight and only appeared after passing perihelion, the closest point to the Sun. It may have broken into several fragments and continues to shed parts, making its behavior even more unpredictable and concerning. Its orbit is approximately 7 million kilometers, very small for a comet, and this proximity raises certain fears, since the closer an object is, the greater the likelihood of unpredictable changes. Public perception of such phenomena is strongly influenced by their unusualness and novelty. In the history of astronomy, there have often been cases where new objects became subjects of widespread discussion because they were unusual, eliciting a vivid emotional and intellectual response. For example, 3 large comets that were recently discovered received significant attention. In this discussion, we will focus in detail on past instances of dangerous celestial body flybys, on asteroids that passed close to Earth with little or no warning, as well as on failures and shortcomings in detection systems, which occur much more frequently than publicly acknowledged or believed. All of this is crucial for understanding the real situation, since delays and errors in detection can have extremely serious consequences. Specifically, we will talk about those asteroids that we managed to detect only when they were already very close to our planet, sometimes even after their passage or at the very last moment. Let's start with one of the most striking examples, an event that took place in early 2025. In January of that year, a celestial body designated 25TF flew past at an incredibly close distance, approximately 400 kilometers above the Earth's surface. To put this in perspective, this distance is significantly less than the altitude of the International Space Station, which orbits at about 250 kilometers. It is also closer than most satellites orbiting our planet, as their orbital heights often exceed 1,000 kilometers. Moreover, this flyby occurred within the orbital zone of numerous space objects in low Earth orbit. And all of this happened completely unexpectedly for us. We had no idea about it until it was almost directly overhead. The asteroid 25TF was very small, its size was likely only a few meters across. In such cases, if it had entered the atmosphere, it would have burned up, transforming into a bright but short-lived light phenomenon, a so-called fireball. This would have been a spectacular flash, causing no significant damage, since its mass and size are too small to cause destruction on the Earth's surface. For comparison, the Chelyabinsk meteorite, which exploded in the air in 2013, had a diameter of about 17 to 20 meters and released energy equivalent to several hundred kilotons of TNT upon explosion. Its blast shattered windows, injured over 1,000 people, and left no crater or visible trace at the site. The 25TF asteroid was significantly smaller, several times so. In this case, everything comes down not to size, but to the essence, the timely detection. The point is that we are not dealing with a large space object capable of causing global damage, but with a small object that, nonetheless, could have been a source of a bright light show and nothing more. The main problem lies in the delay in detection. We did not notice it until it was practically overhead. He flew over a continent considered one of the most remote and sparsely populated on the planet, Antarctica. Very few people observed him there, and the chances of detecting such an object in this region were minimal. Imagine, if he had arrived a few hours earlier or later, or if his trajectory had been slightly different, he could have flown very close to a major settlement without leaving any warning. In that case, the residents would have been left completely unprepared, with no opportunity to take precautions or seek shelter. This is not an isolated incident. In recent years, several cases have been identified where small asteroids were only detected days, hours, or even minutes before their closest approach to Earth. There have been situations where they were only discovered after they had already passed by, or when they were very close, and our systems had not yet registered them. Many of these objects passed by us without any visible signs, remaining undetectable to observation, and were only noticed by accidental observers or automated systems already on their way to Earth. All this happens because our detection network has its limitations. Telescopes and other instruments cannot record everything indiscriminately. They have a minimum detection threshold. Even a relatively small attack on a city can have devastating consequences. Imagine a scenario where the impact power is comparable to a force capable of destroying entire buildings, turning them into ruins and completely destroying infrastructure. In such a situation, even the strongest structures and residential areas could be vulnerable to a powerful blow. And although the atmosphere acts as a kind of shield, slowing down and dispersing part of the energy, it is not an absolute barrier. Objects larger than 20 meters can fall to the ground at a certain altitude, causing dangerous destruction. Smaller objects, despite their lesser mass, can also cause airbursts capable of damaging the environment and inciting panic among the population. Another problem associated with falling asteroids and space debris is the trash left behind after celestial bodies disintegrate. When an asteroid or comet breaks apart in the atmosphere, its fragments scatter over a large area. Most of them are tiny shards, almost invisible, but some can be large enough to pose a real threat. If such debris falls on densely populated regions, they become akin to projectiles capable of causing significant damage. For example, after the event in Chelyabinsk, meteorites were scattered over hundreds of square kilometers, and people collected them as souvenirs, unaware of the full danger. But if the object had been larger or if the fall had occurred at a lower altitude, these fragments could have been much more dangerous. Now, imagine the scale of this threat on a broader level. Instead of a single small asteroid, imagine a cloud of debris formed after a comet's disintegration. Instead of a few meters of rocky material, there are hundreds or even thousands of fragments, ranging from tiny dust particles to boulders scattered along an orbit. Instead of a traditional impact point, this is a dispersed and chaotic threat that is unlikely to hit a specific target but creates a statistical probability of collision. And this probability, albeit small, still exists and should not be ignored. When a comet breaks apart into fragments, it does not produce a single projectile or bullet. It generates an effect similar to a shotgun blast, numerous shards flying in all directions. The distance between Earth's orbit and the comet's orbit, known as the 7 million kilometer interval, is the gap between the trajectories of two celestial bodies. If a comet disintegrates and its fragments disperse along the orbit, some of them may come closer to our planet. It is not necessary to collide directly or even to reach Earth itself. It is enough that the fragments come closer than usually expected. Even a minimal, but non-zero, approach of such debris to our planet becomes a cause for concern. The statistical probability of collision increases with each new fragment, and this is enough for space risk specialists to experience nervous tension. This is a lesson learned from events similar to those of 2025 and other comparable incidents. A delay in detecting potential threats is a serious problem. We cannot see all objects moving in space, small, fast, or following less obvious trajectories. While large asteroids, tracking predictable routes and moving from specific directions, are detected and monitored. But objects that do not follow clear patterns raise alarm because they pose the greatest danger. We can observe those moving predictably, and they cause less concern. However, those that play by different rules, unpredictable and irregular, evoke our fear and anxiety, because we cannot predict or prepare for them. Furthermore, it is worth discussing that danger to Earth may not only come from collisions but also from consequences related to gas emission in space. The release of gases creates a special pressure inside space, acting as an invisible force that separates objects and structures. This pressure arises because, during the evaporation or decomposition of substances in a vacuum, gases are emitted, and their volume or quantity begins to exert force on surrounding surfaces. As a result of this pressure, if it is strong enough, celestial bodies can be destroyed or undergo significant changes. When tidal forces, generated by gravitational influence and the mechanical stresses associated with them, approach massive bodies, they can tear them apart. This is especially evident when these forces exceed the structural strength of an object. Sometimes, with minimal impact, such bodies disintegrate very quietly, small fragments detach and drift off into space, like invisible shards silently scattered along the orbit. In other cases, the destruction is much more dramatic and spectacular. Large chunks of comets or asteroids break into numerous fragments, dispersing in different directions at high speeds, creating a striking spectacle for observers on Earth. One well-known example of such destruction is comet Shoemaker-Levy 9, which in 1992 passed too close to the giant planetary body, Jupiter. As a result of this close approach, under the influence of strong tidal forces, the comet was torn into over 20 pieces. These fragments, orbiting the planet, began colliding with it 2 years later, causing powerful explosions, so-called impacts with Jupiter. These explosions were so intense that they could be seen from Earth's surface. Each impact released enormous energy, comparable to millions of nuclear bombs, leaving significant scars and craters on the planet's surface, which persisted in the atmosphere and on the surface for several months. This event made a profound impression, as it vividly demonstrated how fragile comets can be and how dangerous their debris, flying through space, can cause serious destruction. Another notable example is Comet 73P, Schwarzmann-Wachmann, which underwent multiple fragmentation events. In 1995, it broke into several large pieces, and by 2006, it had disintegrated again into a much greater number of smaller fragments. Observers could see in real time how this comet was splitting into parts, each forming its own coma and possessing its own tail. The fragments continued to disperse, each along its slightly different trajectory. Gradually, these debris formed a stream, a sort of river of ice and dust moving along the original orbit. When Earth passed through this stream, fragments from this debris cloud entered the atmosphere, leading to a temporary and noticeable increase in meteor activity. While not catastrophic enough to cause serious consequences, it was undoubtedly a noticeable and impressive phenomenon. Now, applying these concepts to the comet designated R2, this comet has already experienced one or more outbursts, indicating internal instability and possible ongoing disintegration processes. If it were to split apart, the fragments detaching from it would begin dispersing in different directions. The speed of divergence depends on the nature of the event, on the energy released during fragmentation. It can be gentle when the parts separate gradually and slowly, or intense when a powerful explosion occurs, leading to rapid disintegration. In any case, over time, all fragments will disperse, along with dust that spreads out, forming a cloud of particles that will eventually become hazardous to space objects. The most realistic and serious threat under these conditions is dust. Each comet constantly sheds dust during sublimation, the process of transformation. Imagine a long, winding thread stretching through the vast darkness of space. That is the comet's orbit, moving along its unique trajectory. An important characteristic in this space is the minimum distance between the comet's orbit and Earth's orbit, called the apoid R2, which is 7 million kilometers. This value is critically important because it defines the boundary within which any contact or interaction between the orbits is possible. When a comet traveling along its trajectory undergoes disintegration, it turns into numerous smaller fragments scattered across different parts of the orbit. Imagine these shards flying in all directions, like broken glass fragments or pieces of meteoritic material dispersing along orbits. Some of them, under certain conditions, may approach Earth, not close enough to collide, but close enough for their trajectories to intersect or come near our path. As a result, although these particles do not reach zero distance, they still come close, creating a potential danger. If, at some moment, our planet happens to be in the same region of space where these dispersing fragments are moving, and the timing aligns, the likelihood of collision with streams of cosmic particles sharply increases. In such a situation, we could experience intensified meteor showers, which are usually periodic and not particularly dangerous. However, under special circumstances, this could lead to stronger and more destructive streams than usual. An increase in the intensity of meteor streams can not only create spectacular sights in the sky, bright, fast-moving flashes, but also cause damage to satellites in orbit and even to spacecraft currently conducting scientific missions or providing communication. Naturally, the probability that a single particle will hit a specific object is quite low, since space is vast and targets are tiny points within it. However, overall, the general probability that something will be damaged somewhere significantly increases. Currently, there are a huge number of objects in Earth's orbit, thousands of satellites, space stations, and even primitive spacecraft performing various tasks. All of these objects are potential targets for random fragments moving at speeds of up to 30 kilometers per second. Let us also consider the possible atmospheric reactions. When Earth passes through dense streams of dust and small particles, even if each one is very tiny, their combined effect can be noticeable. In the upper layers of the atmosphere, there is an increase in air luminescence, manifesting as bright meteors and flashes that can suddenly intensify. Amateur astronomers observing the night sky would likely notice such unusual phenomena, record them with meteor cameras, and document abnormal flashes. These events, although not leading to catastrophes, would still be unusual and intriguing, since such phenomena rarely occur without special reasons. The main issue is not the visible dust, small particles that can be seen in the sky, but the fragments we simply do not see. Imagine a large fragment, about 1 or 2 meters across, moving at 30 kilometers per second. Such an object is almost impossible to detect early on, until it approaches Earth or becomes too dangerous. Detecting it with optical instruments is possible, but only if observations are conducted at the right moment and in the right part of the sky. If such a fragment moves from the sun's direction or has a dark surface with low albedo, detecting it becomes significantly more difficult. If it crashes into the atmosphere over a populated area, the consequences could be severe. Imagine a situation occurring in outer space, and try to picture what happens to one of the thinnest and most tenacious threads connecting particles within matter. This thread, once whole and strong, gradually begins to wear out over time. It slowly disintegrates into many smaller threads, each slightly different from the others. Some of these streams remain close enough to the original path of the initial thread and continue to retain a certain resemblance to it. Others, on the contrary, start to deviate and drift away, creating new, more branched paths. Over time, this process transforms the original intact thread into a cloud of numerous thin, scattered threads spreading in different directions, forming a kind of dispersed ribbon extending along the orbit. In this context, Earth's orbit appears as another thread crossing this dispersed ribbon at a certain angle. Most of the time, our planet moves along its path through empty space, where there are no noticeable objects or special phenomena. However, sooner or later, under certain circumstances, Earth crosses this thread-like structure, and at that moment, particles begin to fall out of it. These particles, like drops of rain, fall onto our planet in the form of bright meteor streams, creating spectacular displays in the night sky. Such phenomena are by no means new or unusual. On the contrary, they are classic examples of meteor showers that occur regularly. Perseids, Leonids, Orionids, all these names are associated with streams of debris left behind by passing comets. Every year, Earth crosses these streams, and as a result, we see bright meteors flashing across the night sky. Usually, these events cause only temporary inconveniences, without harm, and often delight observers with their sudden bursts of brightness. However, sometimes meteor showers reach such intensity that they become a true spectacle. For instance, in the 18th century, in 1683, a stunning Leonid meteor shower was observed, during which tens of thousands of meteors appeared in the sky per hour. Witnesses of that time described the sky as being literally filled with fiery light, like a celestial fire covering the entire horizon. If such an event were to occur today, with modern satellite infrastructure, its consequences could be very serious: damage to satellites, communication disruptions, and even potential disasters. Currently, forecasts indicate that the object designated R2 will not produce a meteor storm similar to those of the past. If its debris still exists, it is likely in such small quantities that it would not cause any significant phenomena. However, it is important to remember that in space, we cannot be completely certain that there is no threat until we see it with our own eyes. The sooner we receive confirmation, the earlier we can prepare or take action. Otherwise, our ability to respond will be very limited, and we will remain mere spectators, able only to watch and hope for the best. An important question then arises: are we currently witnessing a real surge of unexpected cosmic visitors? Or is all this just a bias in our observations? Perhaps we are simply starting to notice them better because we pay more attention, or because we have more tools and capabilities to detect such objects. Or, conversely, is the number of celestial bodies approaching Earth truly increasing, and we are only now beginning to notice it? Moving on to the next topic, pattern recognition in astronomy. Over recent years, we have observed a whole series of new, unexpected, and unusual objects. Let me list them to illustrate the scale of ongoing changes. So, in October 2017, the first interstellar object was discovered. When we begin to observe the surrounding cosmos carefully, we realize that our perception is significantly expanding. The deeper we delve into the process of searching for and studying celestial objects, the more new and previously unnoticed details we discover. In particular, the development and implementation of modern observation systems, such as the famous Pan-STARRS Atlas, as well as the upcoming observatory named after Vera Rubin, significantly enhance our ability to detect cosmic phenomena. These systems are designed to record transient events and moving objects that constantly change their position, everything that was previously difficult to notice or remained outside the field of view. As these systems improve and expand, the level of detection of new objects increases. This does not mean that more new bodies are appearing in our near-Earth space environment. Rather, it is a sign that we have begun to see objects that have always been there but remained invisible to our previous methods and instruments. In other words, our ability to observe and record the tiniest details is truly increasing. The second hypothesis that arises in connection with this suggests that the actual flow of objects moving through space may indeed be increasing. Perhaps something within the structure of the cosmos causes disturbances in the comet or asteroid cloud. For example, a star passing nearby, which has long since disappeared from our sight, could have sent a wave or impulse that disrupted the movement of the comet cloud and sent some objects inward toward the system. And only now, thanks to new observation methods, are we beginning to detect the first of these incoming bodies. There is also a possibility that, for some reason, our solar system is crossing a region of space with a higher concentration of cosmic debris and fragments. It is not excluded that gravitational forces and tides within our galaxy, the Milky Way, influence the trajectories of comets, pulling them toward the inner parts of the system. This is quite plausible. The Oort cloud is a vast structure containing trillions of comets and small bodies. Even a small disturbance in the gravitational field can, over a few thousand years, cause thousands of these objects to enter trajectories that bring them into the inner solar system. For our human perception, which is limited to relatively short historical and astronomical timescales, such events may seem like sudden bursts of activity, as if something is being thrown out of nowhere. The third hypothesis, which is no less important, relates to the statistical nature of observed phenomena. Perhaps these appearances are simply coincidences, random glitches arising from chaotic processes. Imagine flipping a coin 100 times. It is quite possible that at some point, a series of heads or tails will occur, which does not indicate any bias of the coin itself or any hidden causes. This is a pure manifestation of randomness, not a pattern. Similarly, 4 unexpected appearances of comets or objects over 8 years can be regarded as statistical noise, a fluctuation that lacks deep meaning or a consistent pattern. In the future, after some time, we may either not encounter such phenomena at all or, conversely, experience 10 or more such events. Without additional data and long-term observations, it is difficult to distinguish a real signal from random noise. Each of these hypotheses has its own evidence and basis, and all require further confirmation. It is important to note that our observations and their interpretations heavily depend on the choice and focus of attention. Over the past 20 years, the number of known near-Earth asteroids has significantly increased. This happened not because there are suddenly more such bodies in space, but because we began systematically searching for them and improving our detection capabilities. Similarly, the situation with comets may be developing along an analogous pattern. For example, a scientist named Swan discovered thousands of comets, most of which are so-called sun gazers, because he has the ability to see them thanks to his instruments that can detect objects invisible to ordinary optical telescopes. Any change in the color of a celestial body indicates alterations in its internal composition or the nature of its surface, which in turn suggests heterogeneity in its structure. Such a spectral shift may indicate that the object is rotating, with different sides reflecting sunlight differently because each may have a different composition or texture. As a result, during rotation, we observe changes in color, reflecting differences in spectral characteristics. It is possible that something is happening in near-Earth space related to gas emission or coma formation, affecting the spectrum of the observed object. Or perhaps the cause lies in something more complex and unusual, which is difficult to judge at this point because we have not yet come close enough to obtain clear answers. Regarding R2, it behaves differently compared to familiar objects. Unlike interstellar bodies, this object is not too distant and does not belong to an extraterrestrial realm. It originates from our own solar system, likely formed in one of the stellar clouds surrounding nascent stars, but it was hidden in solar glare and only appeared after passing perihelion, the closest point to the Sun. This is interesting because it demonstrates how easily we can overlook something, even within our own system. If even objects like R2 can evade our careful observation, then other smaller or less bright objects could also remain unnoticed. How many long-period comets pass through the inner part of our system each year and remain invisible to our instruments? We have no answer to this question. We can only observe those comets that are sufficiently bright and remain visible long enough for our telescopes and instruments to notice them. The rest are ghosts, invisible, unnoticed, fading into the shadows of space. This raises the question, is there some pattern in this flow? Perhaps there is. An optimistic view is that we are gradually improving our ability to see the universe around us as it truly is. And we observe a stream of transient visitors, debris flows, random collisions, unexpected appearances and disappearances of objects. This is evidence that our vision is becoming more accurate and comprehensive, helping us understand that space is not only a calm expanse but also a dynamic environment with constant movement and change. A pessimistic interpretation suggests that the rate at which new bodies and objects arrive is increasing faster than we can track and respond to them. This growth could pose a threat to our safety or scientific research because we are unprepared for such an expansion of the cosmic traffic. A more realistic view likely lies somewhere in between. We observe more because we have become more attentive to the sky, dedicating greater attention and resources to studying it. At the same time, we are beginning to realize that the total volume of space traffic, even with current observation capabilities, remains higher than we previously assumed. Thus, the solar system is not a quiet, peaceful region of space but rather a busy highway constantly populated by various objects in motion. Currently, it's as if we are placing tracking cameras along this highway to monitor everything happening, and soon we will move on to examining the institutional structures managing this movement, data collection and analysis systems, as well as those bottlenecks, silences, and ambiguities that raise suspicion and wariness among people. Next, I will describe how discoveries are transmitted into the publicly accessible knowledge space. When an observer, whether a professional astronomer or an amateur, notices something unusual, a moving object, a bright source, or a transient event, they record its parameters: position, time, brightness. Afterward, they check whether similar reports or observations have already been made. If it turns out to be something new, they report it to the central authority responsible for collecting information about small celestial bodies, the International Small Bodies Center. Data related to near-Earth object observations are primarily public information, accessible to anyone. However, it is important to emphasize that these are raw, unprocessed data that require further analysis. They include elements such as orbital parameters, position vectors of objects, and estimates of their stellar magnitude. Because of its technical nature and complexity, these materials are not intended for a general audience. They are not press releases or news headlines. Primarily, they are internal documents created for astronomers and specialists studying space. Unlike popular news, this data does not attract the attention of ordinary readers or viewers, as most people are not interested in memos from the Interagency Center for Near-Earth Object Observation. They are more likely to focus on news articles and programs that discuss space in a more accessible way. However, such materials appear much later, often with delays, and sometimes not at all. Meanwhile, specialized institutes and laboratories work to refine orbital parameters and assess how dangerous a particular object might be. One such institution is the Jet Propulsion Laboratory, JPL, which uses a comprehensive system called Horizons designed to calculate precise trajectories of objects within our solar system. This system is constantly updated as new observations are made. When astronomers receive fresh data, they reprocess the orbital models, which helps minimize uncertainties and improve forecast accuracy. Accordingly, the more observations and the better the data quality, the more reliable the predictions of an object's future movement become. All this is done to timely evaluate potential risks associated with an object approaching Earth. If there is a possibility that an object could pose a threat and its orbit is approaching Earth, automated monitoring and analysis systems like JPL immediately issue an alert. The Near-Earth Object Center, for example, CENOS, assesses the risk level by analyzing the data and drawing conclusions about the danger. If the risk is sufficiently high, NASA publishes official statements warning the public. Conversely, when the probability of collision or other negative impact is very low, bulletins and reports remain classified within technical databases and are not made public. Let's consider a specific example related to an object designated R2. This object was discovered by amateur astronomer Vladimir Bazuga, who detected it in data obtained using the SWAN system on September 9, 2025. The discovery was quickly confirmed by other observers, who also visually tracked it. Soon after, the Multifunctional Near-Earth Object Observation Center issued an official circular assigning the provisional designation C-2025-R2 to this object. Subsequently, specialists from JPL calculated its orbital parameters, and the CENOS Center carefully evaluated the results. As a result, it was concluded that the object does not pose a threat to Earth. The closest approach to our planet was approximately 260,000 kilometers, which is far enough to consider the situation safe. No press releases or public warnings were prepared as part of this assessment. All information was carefully documented in a technical database accessible to specialists. And now, a certain silence has fallen. Not because someone is hiding something or there is a conspiracy, but because the monitoring system is designed specifically to reduce risks and ensure safety, not to constantly attract public attention. When an object is not dangerous, it does not make headlines, and most people remain completely unaware of its existence. In the case of the R2 object, its mention appears only in a few specialized astronomical publications and on scientific space portals. For example, on September 18, a photograph of this object was marked as the space photo of the day. However, this news hardly elicited any response on social media. Why does our perception of unusual and mysterious lights in the sky seem so sparse and monotonous? What is hidden behind this darkness and lack of clear explanations? When official authorities do not provide convincing answers or outright avoid comments, various assumptions and guesses arise. Among them are conspiracy theories, rumors, and speculation, which quickly spread among the public and raise more and more questions. In this context, it is especially interesting to highlight the case related to Vladimir Bazuga's discovery, which is named R2. This person is not a professional astronomer, nor an employee of space agencies or scientific institutes. He is more of an amateur, passionate about astronomy and capable of analyzing data about celestial objects. And it is precisely thanks to his attentiveness and analytical skills that the opportunity arose to discover the comet earlier than professional scientific teams did. This fact does not imply that there are errors or shortcomings in the work of professionals. Rather, it serves as a reminder that the detection system existing within scientific circles is not entirely closed or impenetrable. It remains vulnerable to extraordinary discoveries because, in the modern world, information about space and observations is a network that is inherently permeable. Sometimes the most important and unexpected discoveries come from unlikely sources and pathways, demonstrating the value of unconventional methods and approaches. However, this also raises many questions. If an amateur was able to discover such an important astronomical find as a comet, which was missed or overlooked by professional researchers, then what are we truly missing? How many other objects are hidden from our view, passing through the inner regions of the solar system unnoticed? Perhaps they end up in the wrong place at the wrong time because our observational programs, surveys, and research are focused elsewhere. Sometimes the sky appears too bright, the weather deteriorates, or technical equipment fails, all of which hinder timely detection of objects. We cannot know for sure how many such cases actually occur, as our knowledge and observations are only part of a large and complex system that naturally gathers and processes information slowly. Checks and confirmations are necessary to rule out false alarms and to prevent panic and incorrect conclusions, but at the same time, this cautious approach sometimes creates gaps and prevents a complete picture of what is happening. These gaps generate doubts, and when people begin to lose trust in official institutions and their information, they seek alternative sources, often filled with unverified rumors or theories. As a result, many hypotheses emerge, including bold ideas, conspiracy theories, and fringe hypotheses that require careful analysis. Still, to avoid confusion and inconsistencies, it is essential to distinguish truly credible assumptions from those lacking solid grounds. Let us turn to a topic that can be called wild cards and conspiracy theories. Allow me to clarify and address this. Many will say that R2 is not a natural object at all, but rather an artificially created device. They claim that it is a probe, a spaceship, or another engineered device sent by someone or something to monitor our world, our planet. There are also those who believe that the trajectory of this object is too convenient, that the timing of its appearance and its path of movement seem too perfectly calibrated, and that its flashes are too controlled and predictable. Some are convinced that NASA and other space agencies know much more than they are willing to reveal to the public, and that hidden information, images, and data are carefully classified. In their view, this is a message, a warning, or even a test meant for us, concealed behind a veil of official information. Many of these people will believe in these hypotheses without questioning their credibility. Let's try to understand and logically sort through these claims. Starting with the first, is it possible that the hypothesis that R2 is an artificial object? The object's trajectory will be tracked with high precision, though minor adjustments are allowed, not related to changes in the composition or position of gases, but rather to technical nuances of observation. Additionally, during observations, electromagnetic radiation, radio signals, infrared signatures, everything indicating the presence of active systems capable of emitting energy across various wave ranges, may also be detected. However, in this case, we did not find any such signals. The entire radiation spectrum resembles that typical for an ordinary comet. The coma, that is, the dust and gas envelope surrounding the comet, corresponds to the sublimation process of ice, where, as it approaches the Sun, the ice turns into gas and creates a characteristic cloud around the nucleus. The object's trajectory strictly follows gravitational dynamics determined by the gravitational pull of the Sun and other celestial bodies. No special signals indicating external control or activity have been detected. The principle of Occam's razor states that the simplest explanation is often the most likely. In this case, R2 appears and behaves like a regular comet, because, most likely, it is indeed a comet. The hypothesis of its artificial origin requires introducing additional assumptions, complications, the involvement of new participants with unknown motives and capabilities. Such a scenario is possible but not necessary. In scientific practice, it is preferable to avoid unnecessary hypotheses and complex explanations if a simpler and more logical one exists. Furthermore, there is an assumption that all images are hidden or carefully controlled. But do we really see everything? Almost certainly not. Modern professional astronomical observatories do not publish all the images they obtain. They process the data, calibrate images, filter noise, select the highest quality frames to present the clearest picture of the observed object. Some data are proprietary to research groups and are not publicly available, as they are intended for internal analysis or specialized studies. Additionally, some data may be of low quality, making them unsuitable for publication. However, concealing information implies a certain intent and coordinated efforts to hide it. This, in turn, requires a level of coordination that is quite difficult to achieve given the widespread distribution of observatories around the world and their independent operations. As for amateur astronomers, who have their own equipment and observational capabilities, if something truly dramatic had occurred in the sky, someone would definitely have published this information. The fact that we do not see any sensational or prominent images suggests that such phenomena simply have not been recorded, rather than someone deliberately hiding them. Now, regarding the hypothesis that the object's trajectory is controlled externally. Could an external force influence the movement of R2? If we interpret this as extraterrestrial beings, then we must admit that it is a hypothesis requiring additional assumptions and evidence. If, on the other hand, we are talking about natural forces, then the answer is unequivocal, yes. Gas ejections create non-gravitational accelerations that can influence the trajectory. Comets are not rigid ballistic bodies. Their movement results not only from gravity but also from the activity of their nuclei, which eject gas and dust as they approach a star. In the case of R2, an actual ejection is observed, indicating that this process indeed affects its path. Models developed by specialists from space agencies and scientific centers incorporate these non-gravitational forces responsible for the release of gases and dust. Although the accuracy of trajectory predictions is not absolute, it is sufficiently high to draw conclusions about the situation. If an object under external control were in an active phase, we would inevitably notice deviations from the calculated trajectories that could not be explained solely by gas emissions. But no such deviations have been recorded. Regarding the fourth point, it is more symbolic and philosophical in nature. Some argue that even if R2 is safe and not, thus, an important question arises: are there claims and ideas that require more careful and thorough consideration? Undoubtedly, yes. Especially worth paying attention to one of the possible threats directly related to the physical properties and behavior of objects in space. First, it is necessary to understand that there is a real possibility that, during the destruction or fragmentation of a cosmic object, fragments and debris could form that pose a danger to the surrounding space. This is not some conspiracy or unfounded assumption. It is a natural consequence of well-known physical laws operating in nature. If, from two initial fragments of a celestial body, parts suddenly break off that deviate from their original trajectory or velocity, these debris could become a source of potential danger. Most likely, this does not involve a direct collision that could lead to a catastrophe, but rather risks associated with space debris, streams of micrometeoroids, and threats emanating from satellites or other artificial objects in orbit. All of this requires constant attention and preparatory measures, since such dangers, although not as large-scale as major space accidents, can still have serious consequences. Essentially, this is a hypothesis based on knowledge of the behavior of comets and asteroids, their destruction, and the formation of debris over long periods of cosmic existence. Regarding the system for sorting and analyzing such potential threats, it can be said that it should be built on strict scientific principles. The artificial origin of objects such as space debris or wreckage cannot be confirmed without supporting evidence. It is also unlikely to remotely assume their artificial origin, given the distributed nature of observations and research that are constantly being conducted worldwide. As for manipulations of trajectories or movement directions of objects, there is no evidence to support such claims, aside from natural gas emissions or other signs of destruction. These signs more likely indicate that the object is subject to natural processes rather than intentional interference. Overall, the presence of fragments and debris that could pose a threat is quite plausible and warrants continuous tracking and monitoring. Speculations on this matter are undoubtedly intriguing, but we must remember that humans have an inherent tendency to see patterns, imagine willpower, and fill gaps in knowledge with stories and conjectures. Nevertheless, it is important to adhere to discipline and a scientific approach, relying solely on factual data to avoid illusions and false assumptions. When information does not support a prevailing theory or explanation, we must be disciplined enough to reject such unfounded hypotheses and move forward without losing a critical perspective. After that, it becomes necessary to shift attention to other topics, as the scientific world constantly presents new interesting headlines and news. Let's examine them in more detail, starting with neuroscience, because the brain is also a complex system with its own features, including blind spots. Specifically, this refers to the fact that, like many other systems, the brain is subject to certain limitations and blind areas that hinder a full understanding of its complex functioning. In particular, the 11th section of neuroscience discusses recent discoveries made at the University of California, San Francisco. Researchers there identified a special protein capable of slowing down brain aging processes. These findings were published in August 2025. The study showed that this protein, present in elderly mice, seemingly plays a role in regulating neuronal aging processes. It influences neural plasticity, that is, the ability of nerve cells to change and adapt throughout life. When scientists blocked the activity of this protein, old mice exhibited significant improvements. Their memory improved, and their learning ability increased noticeably. The neurons in their brains began to function more reliably and stably. The connections between synapses, the results of recent research offer hope and inspire optimism. However, it is important to remember that at this stage, these are preliminary conclusions that require further verification and confirmation. The most significant aspect of these achievements lies in the fact that the potential consequences related to slowing down or even reversing the aging process could be truly vast and profound. One of the most concerning and frightening aspects of aging is the decline in cognitive functions. It is precisely the deterioration of memory, difficulties encountered in learning and acquiring new skills, as well as slowed information processing, all of which negatively impact our ability to maintain independence, preserve individuality, and lead a fulfilling life. If scientists were able to find a way to block a specific protein capable of slowing or completely halting this decline in mental abilities, the implications of such a discovery would be truly colossal. The effects would not be limited to individuals but would extend to entire societies and nations facing the challenge of an aging population. Globally, the economic losses caused by dementia and related diseases are measured in trillions of dollars, highlighting the urgent need for solutions. A treatment that could delay the onset of symptoms by several years, even just 1 or 2, could significantly reduce the burden on healthcare systems, save enormous resources, and, most importantly, spare millions of people from suffering associated with declining cognitive functions. However, serious challenges stand in the way of these possibilities. First and foremost, it is important to recognize that proteins do not function in isolation as separate mechanisms but are part of complex networks, interaction cascades, and feedback systems. Blocking a single specific protein could lead to unpredictable consequences, disrupting the functioning of other systems in the body and triggering a chain reaction that might prove undesirable or even dangerous. In studies conducted on elderly mice, no obvious side effects were observed after intervention. However, the observation period was relatively short, only a few months. The long-term consequences of such procedures remain unknown, and humans are far more complex and multifaceted beings in terms of biological organization. We are living longer than ever before, and during this time, our bodies accumulate more harmful changes, and more associated diseases and pathologies develop. That is why a treatment that shows high efficacy in laboratory models, such as mice, may not always be safe or predictable for humans. Human biology is far more complex and diverse, and what works in one case does not necessarily work as successfully in another. To illustrate, imagine a metaphor. Our brain is a sophisticated detection system that constantly scans the surrounding world, processes incoming signals, creates memories, and makes predictions about the future. When this mechanism functions well and without failures, it detects the tiniest details, quickly adapts to new conditions, and learns from experience. However, with age, its sensitivity gradually diminishes. Signals become weaker, noise appears, making it harder to recognize patterns and hindering proper decision-making. Recent studies conducted by scientists at the University of California, San Francisco, have revealed that a specific protein associated with the processes of brain degradation is part of this deteriorating mechanism. By blocking it, researchers were able to restore some of the youthful sensitivity in the brains of elderly animals, indicating the potential to slow down or even partially recover cognitive functions. Now, let's turn to our astronomical detection systems, telescopes that scan the cosmos, analyze signals, catalog objects, and predict their trajectories. When these instruments operate correctly, they allow us to detect even the faintest objects, such as distant comets or asteroids, warning us of potential dangers to Earth. But even these systems experience failures over time. Instruments age, sensors can become confused, calibration becomes less precise, and data transmission channels become cluttered with noise. As a result, we begin to miss what was once easily noticeable and risk overlooking important signals. Sometimes, the causes of certain problems and failures in the body or system have a specific biological nature. For example, in the case of some diseases, their origin is linked to internal processes occurring within the human or animal body. Often, these involve the accumulation of a particular protein in the organism, which, with age, begins to build up in larger quantities, causing disruptions and impairing the functioning of relevant organs or systems. This protein can slowly accumulate, like ominous dust that becomes thicker and heavier each year, hindering the normal operation of the brain or other organs. Sometimes the cause lies in technological failures, for instance, a malfunctioning sensor or another component responsible for data transmission or process control. When such a sensor fails, the system ceases to function properly, and the resulting issues become apparent at the level of observable symptoms. Additionally, sometimes the problem stems from institutional or organizational factors, where scheduled examinations and preventive measures are conducted irregularly or with gaps, allowing pathologies to develop unnoticed in early stages. In such cases, to find an effective solution, it is necessary first to determine which specific mechanism caused the failure, understand its nature and principles of operation. After that, intervention is needed to correct the situation, restore the system to normal, regain its function, and ensure stability. This approach is universal and always remains relevant across all fields, whether medicine, engineering, or management. Next, I would like to draw your attention to an important topic in neuroscience that generates particular interest. It concerns Alzheimer's disease, as it is one of the most discussed and simultaneously most mysterious diseases of our time. Nowadays, news, articles, and reports regularly appear about possible breakthroughs, suggesting that the disease could be reversed or its progression significantly slowed. That is why it is crucial to understand the basis of these sensational claims and what the real situation behind the headlines is. In this context, it is especially interesting to examine what is known as Part 12, which discusses potential methods for reversing Alzheimer's disease. The time around October 2025 brought another wave of discussion on this topic. During this period, media and scientific circles reported that Alzheimer's in mice might be reversible. Such claims sparked a wave of hope and enthusiasm, as it seemed that scientific progress was moving very quickly and that an effective treatment would soon be found. Articles published at that time were filled with optimism, and social media messages, despite their popularity, created the impression that an unprecedented breakthrough was imminent. However, reality proved to be much more complex and multifaceted. Researchers, through their experiments, tested new intervention methods that could lead to the restoration of brain vessels, removal of amyloid plaques, or regulation of proteins responsible for pathological processes. Variations in these studies depended on the specific methods and approaches used in each case, but the main theme remained unchanged. In elderly mice suffering from cognitive impairments, significant improvements were observed after treatment. Specifically, their brains were cleared of plaques, which are considered one of the main signs of Alzheimer's development. These rodents also showed memory strengthening and an increased ability to learn new information. In some cases, which is particularly interesting, pathological changes completely disappeared, and the disease appeared to be reversed. These instances were not isolated. Over the past 20 years, scientists conducted dozens of studies demonstrating promising results primarily in mice. Such experiments involved developing vaccines capable of destroying amyloid plaques, drugs that reduce the formation of tangled proteins, gene therapies restoring synaptic function, and improving nerve impulse transmission. All these measures showed effectiveness specifically in animal experiments. However, when translating these results to humans, the situation changed dramatically. Most methods that have shown success in mice, modern science often turns into a source of sensational headlines and vivid news stories that instantly capture the public's attention. However, this process frequently results in the loss of an important nuance, a crucial detail that makes understanding complex research clearer and more accurate. Instead of carefully examining the essence of discoveries and their real consequences, the public often leans toward a simplified perception, where the uncertainties inherent in scientific activity are eliminated or ignored. As a result, the gap grows between what scientists have actually discovered or proved and the conclusions drawn or interpretations made by external observers. This gap becomes increasingly noticeable with each new case, especially when ultimately, the treatment promised as groundbreaking proves ineffective, and clinical trials yield negative results. At such moments, people feel betrayed. They were promised hope, told about possible cures and salvation, but instead face yet another disappointment. Trust in scientific research and medicine is undermined, which is particularly painful because these situations evoke feelings of betrayed expectations and a loss of faith in progress. However, this pattern is not a rare phenomenon exclusive to Alzheimer's disease research. It is characteristic of any scientific field where stakes are very high, and the activity itself is extremely complex and multifaceted. Cancer research, climate studies, infectious disease investigations, and even astronomy all face the same problem. Each news story related to a discovery is often presented as a sensation, which later turns out to be more complicated, more uncertain, and more dependent on numerous variables than initially appeared. When astronomers discover a new comet, headlines are filled with words about breathtaking spectacles and unique events visible to the naked eye, creating an atmosphere of anticipation among millions. However, reality is often much more ambiguous. Comets quickly fade in brightness, fragment, break apart, and what promised to be a spectacular sight ultimately becomes a disappointment. The public, expecting amazing views and impressive phenomena, faces the feeling that it was all just an illusion, and the sense of disappointment grows stronger. Such experiences teach us an important lesson: to be skeptical, not cynical. Skepticism implies the ability to critically evaluate news, remain sober-minded and logical, and not believe everything at face value, especially when it comes to bold claims and sensational headlines. When you encounter news about a breakthrough promising radical changes or astonishing achievements, it is essential to refer to the original source. Carefully study the research. Review the sample size on which the conclusions are based. Pay attention to disclaimers, clarifications, and limitations that are always present in scientific works. It is important to understand exactly what scientists measured and what conclusions they drew, as well as to realize that any scientific result is only part of a larger process that requires further research and validation. In most cases, such an answer, the need for continued work, is entirely normal and natural. This is how the scientific method works. Each discovery is just a step on the way to a deeper understanding. However, all these nuances are often ignored in headlines, where the goal is to attract readers' attention and make the material more striking. There, clarity and definiteness are required, while science itself operates with probabilities. A parallel that can be drawn is comparing it to the movement of a comet. The comet itself is real, observations of it are real, calculating its orbit is also real, but brightness forecasts, fragmentation scenarios, all of these are merely probabilities based on modeling, assumptions, and current knowledge. We cannot predict exactly what will happen, we can only estimate the likelihood of a particular event. And most importantly, we must be able to clearly and honestly present these probabilities, without exaggerating or underestimating them, without turning them into certainties. What we perceive today as commonplace and familiar may become outdated in just 2 short years, losing its relevance and significance. Time moves very quickly, and this is not just a feeling but a clear, measurable fact. The development of technology and science does not slow down, on the contrary, it accelerates more and more each day. There are no signs of this process slowing, which causes both admiration and concern. Within global forums bringing together researchers, scientists, and policymakers from around the world, active discussions are underway, and initiatives are being proposed aimed at the harmonious development of artificial intelligence, its alignment with human values and principles. These initiatives differ in details and approaches, but they share a common theme: the need for conscious and responsible development of technology. After all, artificial intelligence possesses power that can be both a blessing and a danger simultaneously. That is why accelerating its development becomes critically important, as we need to ensure that the systems we create meet our real needs and expectations. It is not only about what we seemingly want from AI but also about what it truly should do, based on our values and moral principles. Ultimately, the key question is: who and how makes decisions about the boundaries of AI's capabilities and responsibilities? These are not abstract philosophical reflections, but practical, urgent problems that require immediate solutions. No area of life today remains unaffected by technology. as artificial intelligence systems become more efficient, more autonomous, and integrated into critical infrastructure, the stakes in this game are rising. An error at any stage, whether in medicine, traffic management, or astronomy, can have severe consequences. For example, a mistake in medical diagnosis could lead to a patient's death or serious complications. Reckless traffic management might cause accidents that result in loss of life. In astronomy, an error or oversight in detecting celestial objects could leave us blind to approaching threats, risking catastrophic consequences for humanity as a whole. Today, artificial intelligence is already actively integrated into the tools and systems used in astronomical research, and this is not a theoretical prospect but a real practice. Modern telescopes and automated systems continuously scan and process vast amounts of data. Automated anomaly detection, for instance, allows us to review endless survey images in search of transient events such as sudden outbursts, disappearing objects, or brightness changes. Machine learning helps classify thousands of objects instantly, distinguishing asteroids from stars, comets from galaxies, supernovae from variable stars. All these actions occur in fractions of a second, whereas a human would need minutes or even hours. Algorithms not only classify objects but also refine their orbits by performing a series of positional measurements and calculating future trajectories. They predict possible changes and assess the degree of uncertainty, highlighting objects that could potentially approach Earth. These systems also issue alerts about potential dangers, identifying objects that could pose collision threats and recommending additional observations or inclusion in special lists for further tracking. The volume of data coming from modern telescopes and automated systems is so enormous that manual processing becomes impossible. In a single night, such observations generate terabytes of information, with each image containing millions of different light sources. Each source requires measurements, cataloging, and comparison with existing databases. A crucial task is the identification and marking of transient phenomena, objects that appear, disappear, or change brightness over short periods. In the future, when the Vera Rubin Observatory is fully operational, it will be able to take images of the entire visible sky every few nights. This will enable the detection of billions of celestial objects, of which tens of thousands will be moving, changing, or transiting. Artificial intelligence is undoubtedly a powerful tool capable of significantly expanding the capabilities of modern systems for observing and analyzing space objects. However, it is important to remember that it is not infallible and often makes mistakes in practice. One such mistake is false alarms, situations where the system incorrectly identifies an object as a potential threat or an important astronomical signal, even though there is no real danger or interesting features. For example, during the operation of a cosmic ray detector or a telescope, a bright flash or a bright streak of light may sometimes enter its sensitive element, which becomes distorted or misinterpreted by the system as a moving object resembling a potential asteroid. In such cases, the algorithm quickly detects this object, marking it as a possible threat, although subsequent, more detailed observations reveal that no such object was present at that time and place. It was merely an artifact, a malfunction, a phantom, or simply a misclassification caused by the system's characteristics. Similarly, more complex errors related to data interpretation can occur. For instance, a distant supernova that gradually increases in brightness and becomes more noticeable may be incorrectly classified by the system as a variable star or another type of celestial object. During observations, the light curves of such objects can resemble those of known variable stars, and AI may mistakenly categorize them accordingly. Although such situations may seem minor, in reality they lead to wasted time and resources on further study. It may take several days for a human to carefully review the data, recognize the error, and reclassify the object correctly, but by that time, the optimal observation window has closed. As a result, crucial data or signals that could shed light on new aspects of the universe remain unnoticed or are missed. These failures and errors are particularly dangerous because the system not only fails to detect real anomalies or important signals but also overlooks them, as it tends to ignore unusual or unaccounted cases. Those that fall outside the training data or represent new, previously unseen phenomena. Machine learning relies on examples, and its ability to recognize objects largely depends on the quality and representativeness of the training dataset. If the system is shown thousands of images of asteroids, it will learn to identify them based on certain characteristics: brightness, shape, speed. If it is shown thousands of comets, it will understand what comets look like. But what happens when an object appears in the observations that significantly differs by its nature or characteristics from all those presented in the training set? What if something emerges that goes beyond the usual properties, distortions, or data distributions? In such cases, the system may mistakenly classify this object as noise, a malfunction, or an artifact, or it may completely overlook it because it doesn't fit the pattern. Sometimes, it will incorrectly assign it to the wrong category and attempt to pass it further down the processing chain, which can lead to the loss of an important signal from the researcher's view. Additionally, there is a phenomenon known as training bias. If the original dataset used to train the AI predominantly contains certain types of objects, the system itself will tend to produce biased conclusions. For example, if most data is obtained from optical telescopes studying specific regions of the sky or during a particular season, under certain lighting conditions, the AI will memorize these patterns. It will learn that asteroids generally have certain brightness ranges, characteristic colors, and speeds. As soon as an object deviates from this pattern, for instance, being darker than usual, with a lower albedo or reflecting less sunlight, the system may simply fail to recognize it or reject it. Perhaps this object moves slightly faster or slower than expected, or arrives from an unusual direction, which also doesn't fit the usual framework. As a result, when the false alarm rate becomes significant, the system designed to detect real objects or events begins to struggle. In such cases, it becomes overloaded, like a tired machine unable to cope with the influx of false signals, and as a result, loses the ability to accurately identify genuine threats or objects of interest. In this situation, astronomers dedicated to studying the cosmos are forced to spend all their time and effort chasing ghosts, illusions that in reality pose no danger or scientific value. Consequently, they miss real dangers and signals that could indicate important discoveries or imminent threats. The problem lies in finding the right balance between the system's sensitivity and its specificity. Sensitivity is the ability of a device or system to detect all possible real signals, even the faintest and barely noticeable ones. Specificity, on the other hand, is the ability to reject false signals, preventing them from entering the list of potential objects. The ideal is to achieve both high sensitivity and high specificity simultaneously. However, in practice, this is very difficult to accomplish. Sensitivity, when increased, causes the system to detect more genuine objects, even those that are barely visible, which is very important in scientific research. However, this also leads to a higher number of false alarms, errors, and incorrect alerts that distract researchers and complicate their work. Conversely, if the system is made more specific, it will start to reject most false signals, reducing the number of false alarms. But at the same time, there is a risk of missing important real objects or events, especially those that are faint or unusual. The ideal point is a balance where most real threats and objects are still detected, while false alarms remain within acceptable limits. However, this golden mean is very delicate and constantly changing. It depends on numerous factors: data quality, environmental conditions, characteristics of the objects being sought, their brightness and movement levels. Therefore, achieving optimal results requires continuous system tuning, making adjustments, receiving feedback, and human oversight. This is not a one-time task but an ongoing process that demands attention and skills from specialists. Let's consider a hypothetical scenario to understand how this works in practice. Imagine an artificial intelligence analyzing brightness data of a comet notices an unusual spike in its brightness curve, labeled as R2. For a long time, the comet's brightness was increasing steadily, a logical and expected phenomenon, as it heated up and became brighter as it approached the sun. But suddenly, on October 15, there is a sharp increase in brightness, a minor one, perhaps half a magnitude, yet this spike occurs suddenly, quickly, and sharply, not gradually as all previous models and theories predicted. Such a spike seems unusual and raises questions. What could have caused it? Doesn't it resemble an emotional outburst, a reaction to something unexpected that couldn't be anticipated in advance? But the timing of this spike is strange. It occurs not when the comet was closest to the Sun, but, on the contrary, several weeks afterward, when it was already moving away from the star. This is unusual and sparks serious curiosity. Is such an event real? Or is it merely an artifact resulting from faulty instrument operation? Perhaps the telescope experienced tracking errors or a malfunction in its settings. Or atmospheric conditions changed, affecting the quality of the data collected. Maybe the calibration of the instruments was disrupted, causing distortions. Or something entirely unexpected is happening, something that doesn't fit into the usual models of comet behavior. The most likely hypothesis is that unusual processes are occurring within the comet's physics. A fragment being ejected, a collision with a meteoroid, or a sudden release and explosive ejection of volatile substances from its surface. These events could have been coincidental. At the moment when the observer was reviewing recent images of the night sky, a series of questions and hypotheses already arose in her mind. It seemed that there were some malfunctions with the telescope or detector, or perhaps the weather conditions suddenly worsened, reducing visibility. The observation log recorded clouds, variable cloud cover, and occasional glimpses of clear sky. All of this gave the impression that no significant events or anomalies were occurring at that time. She carefully examined the frames, comparing them to understand what had happened. Thus, she analyzed the images taken before and after the suspected spike. The comet appeared normal in the images, with no signs of damage or unusual structural changes. In subsequent frames, there was no appearance of new fragments or any clear signs of destruction or fragmentation. There were also no indications of sudden brightening that could suggest a luminous event. Everything pointed to the possibility that any spike, if it occurred at all, was likely a transient phenomenon. It could have been a random interference or noise in the data, or perhaps a rare, very short-lived flash that lasted only a few minutes. Confirming its existence would have required other observers working under different conditions and with different equipment, but this did not happen. As a result, the analysis showed that there was no obvious structural change, no new elements, and no signs of sudden brightening or other pronounced alterations. It could be assumed that the spike was merely a brief noise, a random data artifact, or perhaps an insignificant, quickly fading event. In other words, there was a possibility that the event was fictitious and had no real astronomical origin, or it was so brief that it left no noticeable traces. Overall, based on the available data, she concluded that it was most likely a false signal caused by noise or a random malfunction, though the possibility that a real event did occur, but lasted so briefly that confirmation from other observers was impossible, could not be ruled out. In this case, she made a decision. The evidence was inconclusive, and it was impossible to definitively confirm or deny the hypothesis. The spike could have been real, but there was a high probability that it was merely an artifact of the system. Without sufficient confirmation or additional data, it would be wrong and premature to raise an alarm. Such a step would require significant resources, mobilizing other teams, conducting further observations, and coordinating efforts. And if it turned out that the spike was just a coincidence, all the effort would have been in vain. Therefore, considering all the circumstances, she decided not to rush into raising the alarm. The anomaly remained registered in the database, marked as unconfirmed, and ultimately was forgotten, archived as an indeterminate event. Subsequently, it was replaced by the next notification, the next signal received by the system. Everything was functioning as usual, the system continued to operate, processing new data and detecting potential anomalies. But still, what if this flare-up had been real? What if it indicated a fragmentation process of some object, and its parts began to diverge along different trajectories? A human decision made under conditions of uncertainty and limited data could have led to that important event going unnoticed. Time would work against the observers, because to determine whether an object is truly disintegrating, one would need to wait until its parts are sufficiently far apart. In the first hours or even days after the supposed fragmentation, these parts remain very close to each other, making them difficult to distinguish even with high-precision optical devices. Only as they move away from the parent body and the fragments disperse over considerable distances can they become noticeable as a real threat, something that truly matters and could be significant. Such threats are often met with skepticism or disbelief. In most cases, detecting such a danger requires highly precise measuring instruments capable of identifying unusual signals or anomalies. However, these instruments are often few in number because only one happens to be in the right place at the right time to capture an important event. For example, it could be an old, worn telescope built many years ago, which, despite its age and technological obsolescence, managed to detect something worth attention. When a warning about a potential threat appears, it is often ignored or dismissed as noise, not given proper importance. This phenomenon is related to the fact that pattern recognition, which helps humans cope with the overwhelming flow of information, also hinders their ability to notice truly important and rare events. When people become accustomed to the idea that most unusual signals are just false alarms or random noise, they stop reacting to genuine anomalies, creating a certain problem. As a result, the recognition system, designed to assist, sometimes becomes an obstacle because it tends to interpret everything new and unusual as noise or a false alarm, failing to distinguish real threats from random glitches. This is one of the main issues in human-artificial intelligence interaction. No approach or system is perfect. Artificial intelligence is a tool that offers numerous advantages but also has its limitations. It operates very quickly, capable of processing vast amounts of data in a matter of seconds, something that would take a human hours or even days. It can identify patterns that, with careful human analysis, would require significant time and effort. Thanks to this, AI-based systems quickly detect hidden connections, patterns, and anomalies, enabling faster analysis and decision-making processes. This is their undeniable strength. They significantly expand human capabilities when working with large datasets that would be unmanageable under normal conditions. However, artificial intelligence also has notable drawbacks. It never tires, does not lose focus, and is not affected by emotional states that could hinder analysis. It always remains concentrated on executing the algorithms and tasks set by developers. But at the same time, it lacks an understanding of context. It cannot intuitively sense what is truly important and what can be ignored. It is unable to reason about whether a detected anomaly has physical significance or is merely a system glitch. In other words, it lacks an internal sense that helps humans determine what truly matters and what is just random noise. Humans, on the other hand, are slower but very intelligent. They possess knowledge in physics, can interpret data in light of their understanding and experience. They have intuition that helps them make quick decisions based on implicit connections and causal relationships. They are capable of reasoning about the plausibility of findings and whether an observed anomaly corresponds to a real physical situation. But the human brain has its limitations. People are constrained by attention and can focus only on a small portion of information at a time. They are susceptible to fatigue, cognitive biases, and perceptual errors, which can sometimes prevent them from noticing or correctly interpreting important signals, especially if these signals occur outside their current focus. In such situations, the optimal approach is for AI systems and humans to work together, complementing each other. When AI handles scanning and processing large volumes of data, it flags all unusual or potentially important signals and passes them to humans for further evaluation. At this point, humans apply their knowledge, intuition, and contextual understanding to determine what poses a real threat and what is just noise or random interference. This symbiosis enhances detection efficiency and reduces the risk of missing critical signals. In order for such a system to function successfully, it requires conditions of trust, calibration, and more. All models we create for predicting movement trajectories and behavior are complex structures built on a foundation of mathematical hypotheses and algorithms based on vast amounts of data. Just as we design and construct pipelines for transporting liquids and gases, these engineering systems demand careful calculation, planning, and precise execution. In the case of predictive models, it's not only about software algorithms but also about intricate schemes created by humans, trained on datasets that were also selected and prepared by people. All of this is the result of human choice, from selecting the information we deem important to defining the contexts in which these systems will operate. Consequently, biases, gaps in data, and blind spots are not random or natural phenomena but are direct consequences of human involvement in the creation and training of these systems. Sometimes, these biases are deliberately embedded to achieve specific goals. Other times, they are unintentional, arising from the limitations and peculiarities of our perception and thinking. As a result, the systems we develop carry the imprint of our decisions, values, and mistakes. They are not pure and objective tools but complex constructions that embed our choices and constraints. The use of artificial intelligence can help us expand our capabilities, see more than before, and identify patterns that seemed inaccessible. AI is capable of analyzing enormous volumes of data and finding connections and patterns within them, something impossible for humans to do within reasonable timeframes. However, despite all its advantages, artificial intelligence cannot solve the most fundamental problem: the problem of the universe's imperfection and the limitations of our search methods. We seek patterns in the surrounding world, which, by nature, is not specifically tuned to our tasks. The universe is not optimized to reveal exactly the patterns we are looking for and does not account for our human limitations and perceptual peculiarities. This creates additional difficulties. Objects and phenomena we need to detect often appear at the most inconvenient angles, at the worst possible moments, under conditions that complicate their recognition. They may be hidden in bright sunlight or emerge at inopportune times, during bad weather, when visibility is limited, or behave unpredictably, fragment, and change properties in ways that do not match our training data. As a result, detection systems, both human and artificial, must be able to adapt flexibly to these complex and changing conditions. Otherwise, they risk complete failure. Creating more advanced tools is an important part of the task, but no less crucial is another aspect: building effective interaction between these tools and the people who use them. Only in this way can more accurate and timely object detection be ensured, along with correct interpretation and decision-making based on the data received. Ultimately, success depends not only on the technical perfection of the systems but also on how well humans and machines can work together, complementing each other. Next, to gain a deeper understanding of the nature of degradation in detection and perception systems, we turn to neuroscience research, which allows us to use the metaphor of aging and deterioration to describe this process. In particular, in one of the latest publications dated October 3, 2025, researchers from Stanford University shared the results of their study on the decline of spatial memory in elderly people and animals. In this research, scientists focused on neurons in the hippocampus, a brain region that plays a key role in forming what are called cognitive maps of the environment. These cognitive maps are not just abstract schemas. They are real neural representations of physical space, formed based on experience and repeated exposure. They serve as internal mental schemas that help animals and humans orient themselves in their surroundings, know where they are, and quickly find their way to a target point. In a young organism, hippocampal neurons activate reliably. Synaptic plasticity is the remarkable ability of neural connections to strengthen or weaken in response to experience and external influences, forming the fundamental basis of learning and memory processes in our brain. This unique capacity allows neural networks to adapt to new conditions, updating their maps and interaction schemas. When plasticity decreases, neurons lose the ability to flexibly and promptly re-evaluate their connections, correct errors, and incorporate new information. As a result, the internal representation of the environment becomes distorted, as if the map has become tangled, outdated, and unreliable, despite still existing as some kind of schema. Humans or animals can still navigate their environment, but their accuracy is significantly reduced. They make more errors, give incorrect assessments, and choose wrong directions or methods of action. Consequently, the time required for goal searching and orientation increases. This process becomes more complicated and stretched out. This decline in plasticity occurs gradually, literally drop by drop, and is difficult to notice at first. However, with closer inspection, this manifestation can be measured and documented. Over time, this tendency intensifies. Errors begin to accumulate, and the internal mapping system starts to deteriorate, losing its relevance and accuracy. This phenomenon is not limited to neuroscience. It serves as a powerful metaphor for any type of detection system we have ever created or used. For example, telescopic systems, complex instruments designed to observe distant stars and galaxies, also age and lose their original precision over time. Initially, these devices exhibit exceptional clarity, high resolution, and accurate calibration tuned to detect even the faintest signals. But as time passes, their quality begins to decline. Gradually, micro shifts and drifts develop in the optical system, initially barely noticeable, but eventually leading to image degradation. The main causes are mechanical and thermal changes. Mirrors intended to focus starlight are mounted on structures that expand and contract with ambient temperature fluctuations. Over months and years, these mechanical deformations accumulate, causing the focus to soften and the image quality to become less sharp. Light that was once concentrated into a pinpoint now disperses across multiple elements. As a result, the point spread function, describing how the telescope visualizes a single point source, becomes more complex, and the system's resolving power diminishes. Additionally, dust and contaminants accumulate on mirror surfaces over time. Even in the most modern and carefully protected observatories, where hermetic conditions are maintained, particles still settle, scattering light and reducing the number of photons reaching the detectors. All of this leads to images that are less bright and less sharp. Environmental factors, wind carrying sand, temperature changes causing moisture condensation, further accelerate the degradation of optical surfaces. Oxidative corrosion of mirror coatings is particularly dangerous. Aluminum coatings used for reflecting light oxidize over time, causing the reflectivity coefficient to decrease. Initially, it is about 98%, then drops to 95%, and eventually to around 90%. Each shift, each lost percentage, means fewer photons are reflected by the mirror, thereby reducing the system's sensitivity. As a result, faint objects that should be clearly visible begin to fade or disappear altogether, and observational capabilities deteriorate. Ultimately, to restore the original performance, the mirror must be dismantled and a new layer of luminescent coating applied. A process that takes weeks or even months and costs hundreds of thousands of dollars. Problems also arise with the sensors that serve as the eyes of the instruments. In modern devices utilizing silicon chips, the data that once formed the basis for precise measurements gradually disappear and lose their relevance over time. The calibration process becomes less reliable than before, and regular recalibration is necessary to maintain the quality of scientific results. Every modern telescope requires periodic calibration, a procedure that converts raw signals from detectors into understandable and meaningful measurements. During this process, the telescope is aimed at stars with known brightness, and the resulting signal is measured. Based on these data, a so-called calibration curve is constructed, which serves as a reference for subsequent measurements. However, over time, this calibration curve begins to drift, the detector's response changes, its sensitivity to light may decrease or increase, and the parameters of the optical system or atmospheric conditions affecting the signal's passage can also vary. If regular recalibration is not performed, the accuracy of all subsequent data will gradually deteriorate. An object that you estimate to have a magnitude of 6 may actually be slightly brighter or dimmer. For example, magnitude 5.8 or 6.2. This uncertainty propagates to all subsequent measurements, making brightness estimates less reliable and precise. As a result, the accuracy of predictions based on this data diminishes, especially when modeling the behavior of objects or forecasting their future characteristics. Orbital calculations that depend on precise brightness values become less trustworthy, and the level of errors and inaccuracies increases. Visual images captured by the telescope begin to appear more blurred and fuzzy because the optical system's quality degrades and the ability to distinguish fine details diminishes. The detection threshold for objects rises. Objects that were previously easily noticeable and yielded confident observational results now find themselves at the edge of statistical significance. Under such conditions, it becomes difficult to determine whether it is a comet or a noise spike, a moving object or a random glitch caused by cosmic rays. The uncertainty in the data grows, and observers start to doubt the correctness of their interpretations. This leads to the need for additional observations even for the most minor discoveries, complicating the system's operation and creating a queue of tasks. Consequently, objects that were previously detectable and identifiable may escape before they can be confirmed. We begin to miss the unique discoveries that were once possible under good conditions and with high data accuracy. Technical maintenance helps address some issues, but its capabilities are limited. For example, mirrors can be wiped or gently cleaned of dust using a soft cloth or compressed air to avoid damaging the surface. However, such cleaning carries certain risks. Scratches, stains, or marks may appear, which could degrade the mirror's performance. Restoring the mirror's reflective properties is achieved by reapplying a protective coating. To do this, the mirror is removed, sent to a specialized facility that applies such coatings, and waits several weeks for this complex technological process to be completed. The mirror is then returned, reinstalled, and precisely aligned and calibrated. This entire process causes downtime. During the repair period, observations are completely halted, and any objects that could have been detected during this window remain unnoticed and are entirely missed. Another problem is that modern sensors and instruments become outdated or fail over time. They can be replaced with new devices that have higher quantum efficiency, lower noise levels, and an extended dynamic range. Such technological solutions are already available, however, their acquisition and installation require significant costs. The price of a single modern detector can reach millions of Russian rubles. Installing this equipment demands high precision and careful handling, and to reduce thermal noise, it must be cooled to cryogenic temperatures, which adds complexity to its operation. Maintaining the cooling system in working condition requires regular adjustments. Deviations in measurements often go unnoticed and hidden until someone conducts a thorough check and discovers that the data are incorrect or distorted. By that time, a considerable amount of time, weeks or even months, may have passed, during which critical parameters were collected and recorded. It then becomes clear that all the obtained data were based on erroneous calculations or incorrect information, and the consequences can be quite serious. Based on these distorted data, forecasts are made regarding the positions and trajectories of objects, orbital paths, which, in turn, begin to contain errors. If the initial error was significant, it gradually propagates forward like a chain reaction, affecting the entire system. As a result, objects in space are positioned incorrectly, and the predicted forecasts become unreliable. Research and predictions built on such data do not materialize or meet expectations. However, maintaining and servicing these complex systems require substantial resources, financial, human, temporal, and professional. Budgets allocated for such work are often limited and frequently do not allow for the necessary level of equipment care. Organizations that fund research tend to prefer investing in new missions and the development of new technologies rather than supporting and repairing existing, outdated systems. Once a telescope or another complex instrument is put into operation, a period of active use and research begins, after which interest and excitement about its capabilities gradually fade. The initial buzz around updates and new findings also diminishes over time. The scientists who created or led the development of the instrument retire, taking with them their accumulated experience and knowledge. Engineers responsible for its assembly and launch move on to new projects, leaving the old equipment behind. As a result, the institution housing the instrument ends up with a system that is outdated and no longer meets modern requirements, along with diminishing financial support. Maintenance of the system is postponed, as are updates and upgrades. Over time, the technical condition of the equipment deteriorates faster than it can be restored or repaired. The process of degradation accelerates beyond the system's capacity for recovery, and ultimately entropy, the natural process of destruction and decay of complex systems, prevails. Studies conducted at Stanford show that even biological systems, capable of self-reproduction and constant regeneration, eventually begin to decline over time. Neurons in the brains of humans and animals lose their functionality, despite the remarkable ability of the brain to create new synapses, eliminate unused connections, and reorganize neural networks. One of the few areas of the brain where neurogenesis, the formation of new neurons, continues throughout life is the hippocampus. This process persists even in elderly individuals, offering hope for regeneration and support of cognitive functions. Nevertheless, even with this regenerative capacity, over time, spatial memory tends to decline. New neurons cannot fully compensate for accumulated damage and wear. Synapses gradually weaken, damaged or malfunctioning proteins build up, and memory maps become less reliable and precise. The degradation process proceeds more slowly than it would without regeneration, but it is inevitable. Just as the human body ages, even the most carefully designed and self-regulating systems ultimately wear out. Our astronomical instruments are complex, high-tech devices created by humans, and they do not possess self-healing properties. They cannot regenerate damaged components or recover from wear on their own. Damage inflicted remains until human intervention occurs. And such intervention is labor-intensive, costly, and often incomplete. For example, a mirror cleaned today may be covered with a thin layer of dust or dust particles tomorrow. Or a sensor replaced with a new one will, after some time, begin to accumulate errors. One of the important aspects of working with observational instruments is the fact that the results obtained using the same device can vary significantly depending on its current condition and technical state. In other words, the same object observed with identical equipment and under the same conditions can yield different results if the equipment is not in proper working order and fully functional. This is not a hypothetical situation or a mere theoretical assumption. Such situations occur constantly. In recent years, with the development and improvement of survey telescopes, it has been noted that the number of objects they detect decreases compared to the initial period of their operation. Although the sky does not undergo significant changes over a short period, the reason for this trend lies in the deterioration of the instrument's technical characteristics. During operation, equipment gradually ages, optical quality declines, sensor malfunctions and data processing system failures occur. All of this leads to the instruments becoming less effective, and if we do not account for these factors, do not perform timely calibration and regular testing, we risk missing important objects or phenomena. This happens because the data obtained from such instruments lose the features that previously allowed their detection. We simply do not see them. They are like ghosts, invisible to our instruments and processing methods. They remain undetected, unseen, and we are often unaware of their existence. Additionally, there is another form of degradation, a decline in the quality and completeness of the data itself, known as data fatigue. Modern telescopes and observation systems generate incredibly large volumes of information. For example, contemporary wide-field imaging systems can produce data at the petabyte level annually. Each image contains millions of pixels, and each pixel is a separate measurement, a fragment of information about the observed object or region of the sky. Processing such a massive dataset requires complex automated systems, called data processing pipelines, which must automatically identify sources, precisely determine their positions, calculate brightness and other parameters, perform cross-referencing, organize the obtained information, and flag any anomalies. These automated systems operate continuously, constantly ingesting new data and producing results that are then used by researchers. However, as the volume and flow of data increase, so does the load on these automated systems. The processing time for each new image lengthens, causing delays. As a result, large amounts of data accumulate, and processing becomes increasingly time-consuming. Today's image can only be fully processed after a day or even several days following its acquisition. It is precisely at the moment when a person, specialist, or researcher notices a potential anomaly or an interesting object and decides to take action that the situation may have already changed. The object that was just recorded may have already shifted or disappeared beyond the horizon, and the observation window may have closed. As a result, we lose the opportunity to confirm its exact position, refine its orbit, or assess the potential risk associated with that object. Another bottleneck in the observation and data storage chain is long-term data retention. This requires complex infrastructure, storage systems, hard drives, servers, cooling systems, redundancy, and data backups, all of which entail significant costs. When research budgets are cut, the available funds for data storage naturally decrease. Old, already processed and archived data are often transferred to slower media, such as tape drives, which can take several hours to access. If there is a need to reprocess an old image or find an object that was blurry or missed the first time, one must wait for the necessary tape to load and for the data to be transferred to the system. This process can take a lot of time. Sometimes entire days pass before reprocessing can begin. By that time, the object of interest may have already disappeared or shifted, and the opportunity to accurately record it or assess the risk has been lost. Maintaining high efficiency in observation systems requires not only functioning equipment but also constant operation of software, procedures, and the accumulated knowledge and experience of specialists. Software systems always carry the risk of errors or unforeseen issues. When dealing with complex systems such as telescopes or other high-tech devices, it is important to understand that any significant changes to their settings or components can lead to a loss of accuracy and efficiency. Conversely, making only minor adjustments, trying to fine-tune parameters to eliminate errors or false alarms, often proves to be futile. As a result, false signals and errors continue to occur, creating ongoing difficulties for operators and engineers. That is why the maintenance of such systems should be entrusted to a team of experts with deep knowledge, extensive experience, and understanding of all the nuances of the device's operation. These professionals know how to properly configure parameters, test results, and troubleshoot issues based on their expertise and practical experience. Unfortunately, over time, such specialists retire or leave for other reasons. Consequently, they are replaced by new staff who do not possess an equally profound understanding of the system. Engineers who designed the device, those who understood its features and knew about the existing, blind spots, areas that are often overlooked, all of them gradually disappear from the maintenance process. Documentation helps preserve some of this knowledge, but it can never fully replace live experience and intuition, which only come with many years of work. When a new team takes over, they encounter the system which they study but do not know thoroughly. They lack an intuitive understanding of why certain decisions were made and cannot always foresee the consequences of their actions. As a result, errors occur more frequently than desired. Parameters are changed without fully understanding their impact, calibration files are updated incorrectly, and previously questioned and rejected assumptions are reintroduced into operation. All of this leads to the system gradually losing its optimal performance. Object detection rates decline, efficiency drops, but none of the new specialists notice this immediately. Usually, the problem is identified only during retrospective analysis, when it is discovered that the telescope is missing objects it should detect reliably. This process can be likened to the functioning of the human brain, which ages and degrades over time. Both, the system and the brain, begin to operate with reduced sensitivity, lose the ability to respond to signals, and require constant care and support to slow this gradual decline. Ultimately, despite all our efforts and maintenance, systems inevitably reach a point where they cease to function properly. They fail, and often restoring their operability involves the same actions as repairing any complex mechanism: performing repairs, recalibration, modernization, replacing worn components with new ones. The most important task in this process is to train a new generation of specialists, passing on all accumulated documentation and knowledge, and forming an institutional memory that will help preserve experience. At every level, it is necessary to combat entropy, the natural destruction of order that inevitably occurs over time. Understanding that it is impossible to completely defeat this tendency helps focus on delaying its manifestations as long as possible. This is where our hope lies, to slow down degradation enough to leave time for important discoveries and decisions. Research conducted by scientists at Stanford University showed that blocking aging-related proteins in mice helped restore some of their spatial memory functions. However, it is worth noting that such interventions do not turn old animals into young ones. They only make them less old. This slows down their aging process, allowing extra time during which the organism functions better than without such support. The same principle applies to the maintenance of telescopes. It does not restore the device to its original, like new condition, but merely slows down its degradation. This enables extending its service life, buying time for more serious repairs or upgrades, and preparing the system for future challenges. It is time to look for the next, unexpected object. If we consider R2 as a signal indicating the need to take specific actions, then a clear roadmap opens up before us, showing the direction in which to move to ensure safety and obtain the most comprehensive information about the approaching comet. The closest approach of this cosmic visitor to Earth is scheduled for October 24, 2025, that is, 8 days from now. On this day, Comet R2 will pass at a distance of approximately 26/100ths of an astronomical unit from the surface of our planet. All efforts, observations, and measurements should be concentrated during this short time frame to understand its behavior and properties as accurately as possible. However, besides this important event, there is a whole set of tasks that require constant attention and careful preparation. First and foremost, it is necessary to update and precisely refine ephemerides, special tables that record the positions of celestial bodies in the sky at any given moment. This means tracking the trajectory of R2 daily, or even several times a day, continuously monitoring its movement along its orbit. Equally important is refining its orbital parameters, taking into account the influence of various factors and perturbations that could slightly alter its path. In particular, close attention must be paid to the gas emissions from the comet, as these create non-gravitational forces capable of slightly deviating its trajectory. In cases of repeated outbursts or asymmetric ejections, which may occur due to the comet's internal activity, its movement could change a bit more than expected, possibly enough to affect forecasts and future path calculations. Therefore, measurements must continue without interruption, and methods should be constantly improved. It is not correct to consider current results as final or definitive. All parameters require ongoing adjustments and refinements. The second important task relates to spectroscopy and radar reconnaissance. These methods provide insights into the internal structure and composition of Comet R2. Spectroscopy allows us to determine which gases are emitted from the coma, the clouds surrounding the nucleus, and which molecules are present in its composition. This is crucial for understanding the nature of the object, its chemical and physical state. If a comet passes close enough and there is an opportunity to direct specially tuned radar antennas at it, the radar will be able not only to distinguish the nucleus but also to measure its exact size, determine its rotation characteristics, and, with a fortunate combination of circumstances, even observe its internal structure. This data is not merely scientific curiosity, it is vital for predicting the comet's behavior and assessing potential risks. The more we know about the composition of the nucleus, the better we can understand how it will react to solar heat and solar wind. For example, a nucleus rich in volatile substances will emit more gas and dust, increasing the likelihood of active outbursts. The structure of the nucleus also plays an important role. A pile of debris loosely connected can easily break apart under external forces, while a monolithic body will remain intact and retain its shape. Therefore, it is necessary to determine whether the nucleus is a solid, hard chunk or a loose collection of debris to predict its future evolution. The third task involves obtaining high-resolution images. Cameras and optical systems must be configured to attempt to resolve the comet's nucleus into separate parts and to detect possible fragments. If, during the approach or study of Comet R2, the nucleus splits or processes of dispersal of its parts begin, it is important to record this now, while there is still an opportunity. The earlier we detect and document these fragments, the better we can calculate their trajectories and predict where they might go in the future. Initially, such debris disperses very slowly, and at this moment, we have a chance to capture them and determine their parameters. The sooner we react and record their movement, the more accurate our forecast of subsequent events will be. The fourth task is monitoring dust and debris that may be ejected from the comet. It is necessary to analyze the paths along which these particles travel, and modern policies and existing safety systems require us to have clear and specific requirements for the institutions responsible for protecting our planet and ensuring its safety. First and foremost, it is essential to invest in the development and improvement of observation systems for solar panels and space objects moving near Earth. In this area, it is critically important to expand the capabilities of tools designed for detecting and tracking potential threats. For example, most of our telescopes are currently oriented away from the Sun, which seems natural. The Sun is too bright, it blinds sensors, and observing it is difficult. However, precisely because of this approach, objects approaching from the Sun's direction remain invisible in the early stages until they appear in the field of view. Therefore, it is very important to create space telescopes specifically designed for observing the Sun and its surroundings to avoid missing potentially dangerous objects. Devices like WardSide, capable of detecting comets and asteroids in bright light, have already proven their effectiveness. One successful example is the SOHO Swan satellite, which demonstrated that these technologies work. We need to expand the fleet of such devices to cover as much of the spectrum as possible and ensure timely detection of new celestial bodies. Secondly, it is crucial to create open and accessible data transmission channels that operate in real time. Transparency in data processing significantly reduces secrecy and eliminates the shadow of conspiracy often caused by the lack of timely and understandable information. When observation results are published without delays, when orbital solutions are updated instantly, and uncertainties are clearly indicated, trust in safety systems increases. People do not need to make guesses or assumptions, as all necessary information becomes accessible and comprehensible. Currently, the Small Planet Center and the Jet Propulsion Laboratory are taking initial steps by providing some data to the public. However, the interfaces of these resources are often complex and technically dense. We need to develop more user-friendly and understandable dashboards, visualizations, and summaries that are accessible even to those without specialized training. Make the data as transparent as possible, explain it in simple words so that everyone can understand what dangers may be lurking in space. The third important component is international coordination. Telescopes located around the world form a global network for monitoring celestial objects. Different time zones, capabilities, and features of each observatory add complexity, but such a real-time network can provide continuous tracking of potentially dangerous bodies. When one telescope, beyond the horizon, loses sight of an object, another automatically continues observing it. An important aspect is the standardization of alert protocols. How quickly does one observatory share information about a potential threat with others? How promptly does this information reach decision makers? Time is our most valuable resource. Minutes, let alone hours or days, can be decisive. For comparison, consider Apophis, an asteroid known as 99,942 Apophis, approximately 340 meters in diameter. It will pass very close to Earth, at a distance of less than 31,000 kilometers, much closer than some communication satellites in geostationary orbit. This event is scheduled for April 14, 2029, less than 4 years from now. We began tracking this asteroid back in 2004, so we have been observing it for over 21 years. During this time, we obtained precise data about its orbit, determining with accuracy to within a kilometer where it will be at the moment of closest approach. We can confidently say, it will not touch us. We know for certain that it will pass at a distance of approximately 31,000 kilometers, closer than some satellites, yet still safe for Earth. This gives us enough time to prepare, deploy the necessary instruments, and conduct additional research as the object approaches. In this case, we are dealing with a predictable event. Time is the most valuable and irreplaceable resource in the field of space defense, as it determines our ability to respond and protect our planet. Time is the opportunity to observe celestial objects, their movements, and changes, which can be critically important for Earth's safety. It is now time to refine the trajectories of potential threats more thoroughly, since even a small deviation or error in calculations can have far-reaching consequences. Time is also a chance to evaluate all possible scenarios, weigh risks, and prepare appropriate measures. When time runs out, all possible scenarios disappear as if dissolving into space, leaving only the hope and prayer that our predictions come true, that uncertainty does not lead to catastrophe, and that all fragments resulting from a collision do not disperse into orbits crossing Earth's. Particular attention in this context is given to predictable large objects passing near our planet. These astronomical bodies evoke both interest and concern, as their detection and study are of utmost importance. The Apophis asteroid will become the subject of comprehensive investigation, all telescopes will focus on it, and all radars will track its movement. In just one flyby of this celestial body, we will learn much more about space rocks and their characteristics than in decades of remote observations. This is an important and valuable achievement, since in most cases, it is such fast and bright objects that attract the close attention of scientists. But at the same time, there is a danger posed by objects we cannot see. Small in size, very fast, unpredictable, capable of appearing suddenly and hiding in bright light, they can emerge from unexpected angles and sharply increase their brightness when we are distracted or looking away. These objects, invisible in early stages, pose the greatest threat. They can catch us off guard, because the universe does not seek to kill us or save us. It is completely indifferent to our fears and expectations. Objects move along cosmic trajectories under the influence of gravity and momentum, and some of them cross our path. Most, however, miss us entirely, only a few enter the dangerous zone. This distribution is the result of statistics. In short time frames, collisions happen randomly, while over longer periods they become predictable and follow certain patterns. We live during a brief window when the risk of collision is low enough for civilization to exist and develop, yet high enough to warrant monitoring and taking precautions. The consequences of a strike similar to the one that wiped out the dinosaurs occurred approximately 66 million years ago. At that time, an asteroid about 10 kilometers wide traveling at roughly 20 kilometers per second released an amount of energy equivalent to billions of nuclear bombs and created a crater about 200 kilometers in diameter. The explosion threw a vast amount of debris into the atmosphere, darkening the sky and ushering in a long, difficult era for Earth. Such a catastrophe ended an entire era and serves as a stark reminder of the potential consequences of cosmic collisions. Although today such an event seems unlikely, it remains possible. Perhaps not today or tomorrow, and most likely not in our lifetime, but ultimately, the question is whether we will see that moment, whether we will be prepared to act, or remain passive like the dinosaurs, unaware of the danger until the sky ignited. A small but dangerous object like R2 would not be an apocalyptic event for humanity. It is too small, too distant, and too well studied. However, its appearance is a kind of test, a check of our detection and response systems. It is a test of our ability to notice threats in time. Let us question these stories and assumptions. Do not rush to accept everything at face value, stay curious and think critically. Our universe is full of mysteries, astonishing phenomena, and potential threats. Most of the miracles happening around us can be perceived as pleasant and even inspiring, because they occur so rarely and so delicately that we can safely enjoy their beauty and uniqueness. However, we must remember that dangers do not announce their arrival in advance. They require no permission or consent. They simply appear suddenly and without warning. That is why, when it comes to potential threats from space, our only chance to survive and avoid catastrophe is the quality of our detection systems and the speed with which we can respond to an emerging threat. There are only 8 days left until the closest approach to the object codenamed R2. During this time, we are carefully monitoring its movement, collecting data, and analyzing the situation. Current indicators and figures suggest that we are in a safe zone at the moment, and the risk seems minimal. However, numbers alone cannot provide an absolute guarantee. They are merely mathematical estimates, probabilities expressed in equations that sometimes surprise with their accuracy and unexpected results. For this reason, we continue to look to the sky, constantly perform calculations, and model scenarios for development. This is part of our responsible work, because ignoring threats means exposing ourselves to danger. We build powerful telescopes, train astronomer specialists, fund scientific research, and organize international cooperation. All of this is done to be prepared and to know as much as possible about potential dangers. Because, ultimately, the only alternative is complete ignorance, and ignorance often turns out to be far more dangerous than the objects themselves that may pose a threat. Space is not a lifeless void, it is filled with debris, trash, alien bodies, visitors, and wanderers who sometimes accidentally or intentionally find themselves within our sphere of influence. Most pass by without causing harm, but some are capable of inflicting significant damage or creating dangerous situations. Object R2 serves as a reminder that our region is not a quiet haven, that there is movement in space, that danger is real and always present, albeit small. It also demonstrates that risk never reaches zero, and that is why vigilance is not a sign of paranoia but an essential part of survival. Keep observing, analyzing, and being prepared for any situation, because only then can we maintain our safety and ensure the future.